Hello, everybody. Welcome to our second day of sessions at Beam College. Um, we have a packed day with lots of stuff, and we will start with some hardcore stuff. It's a pleasure to be here with Reza Rokni and Amit Altai. Uh, Reza joining us from Singapore, Amit joining us from US West Coast. So we were saying that we have quite a large gap of time zones between our instructors today. Thank you very much for being so late, Teresa, and so early, Amit.
Well, it's actually early for me now because I'm now in Friday.
Yeah, thank you. So, okay, let's start. We will be doing a collab. This is a hands-on practical session, demo slash hands-on lab. So, Reza will explain how to open the collab. And without further ado, please carry on.
Yes, thank you very much for that intro. And Ahmed is will be helping us with questions and stuff as we progress. So, in order to access the CodeLab and follow along as I go through this, you can go to the site that you've been provided, and under day two, go to B1 Beam College in this rather long file name that I've chosen to use. In order to open this, you can actually right-click and open in a new tab. I understand if you actually try and open it within here, it's quite a big file. It doesn't open. So if you right click and open a new tab, it should open up in CodeLab, and you can then follow along. Oh, I'll just reconnect here. So what we have done here is try to do something slightly different, just because normally with Windows and triggers and the complexity of how that all interacts with the watermarks, it can be quite a steep learning curve. And we often do sort of conceptual slides, and then we do the labs. In this one, we try to put everything together. So it is a long notebook. I'm not sure if we're going to get all the way to the end by the end of the session, but hopefully it's standalone, so you could continue if you wanted to. The other part of this is there is a lot of writing on this notebook. You don't need to read it as I'm scrolling through. I'm actually going to be walking through things and going through the various cell points, cell code pieces. Um, in terms of what we're going to cover, so we're going to start on some basics around timestamps and sources, looking at how we can introspect various elements within the pipeline, give you some tools for around how you do debugging and actually try to reason out what this pipeline is doing. We're going to look at how windows are assigned, and we're going to do that firstly mostly in a batch simulation. After that, we're going to move some more advanced stuff, which is on the stream processing side. We're going to talk about event time, processing time, look a little bit at the watermarks, etc. And for that, we're going to be simulating a streaming pipeline using the test stream utility. For this, to help save time, I've actually pre-run all of the cells for my CodeLab, but of course, if you wanted to try that yourselves, you could just run them as we go. When you come to do the setup one, on the install, you might find there are some errors. They should be benign, and if you continue and click onto the rest of the cells, everything should be fine. So we'll skip past these first two, which are just the setup and some imports. So let's start lots going through this and thinking about timestamps and how that's assigned on various sources. So for the very first one, we're going to do a batch pipeline. And throughout this CodeLab, we're going to make use of a simple data set. What we're going to simulate is stock ticks from the stock market. These would normally come with a value, for example, $1.05, an instrument, which is just a string identifier, and a timestamp. So that's the values that we're going to use and we're going to put into this array. If you notice, for now, I am not putting in any timestamp information. The array happens to have these ticks that have come from the market in the correct order. So the order is correct within this array. And we have a value for the instrument ID of being A. Essentially, we're going to ignore that from this point onwards because there is only one value. All the computations and aggregations we're going to do is only going to be for one key. And we've done that to just keep things nice and simple. So the first thing that we do is a Beam pipeline. So hopefully from day one, you'll be familiar with this, with the Beam pipeline as P. We are going to use the create transform, which allows us to use this array of information. And of course, even though I put all the information into this array ordered, the moment we use create, it's going to create a P collection of unordered data. So we can no longer rely on the order that existed in the array. This will then be sent to the transform that we're going to use throughout this process, which is a combiner. It's going to aggregate everything up and count the number of elements per key. In this particular instance, there is only one key. There are 6 elements in here, and the output that we'd expect from this is to be 6. So as I said, I've already run these before. The count is 6, is the output that we have. We can ignore these final 2 transforms. These are just to pretty up our results. Now, we didn't provide any timestamp or windowing information in this little batch pipeline. However, Beam always assigns windows and timestamps. And for us to be able to look at this data a little bit more closely and introspect the elements in more detail, we need a little bit of help from some helper functions. And for that, I've created a couple of utilities that we're going to use throughout the process. So I'll spend a couple of minutes talking about this. The get element timestamp is a class for is a dofun that we've created. We'll ignore this particular piece for now, which is the pane info. So this is a dofun that we created, and in the process piece, we are accessing various pieces of information. And these tools are very useful whenever you're looking at why a pipeline might be acting strange, or why things aren't behaving the way you were thinking. I usually do my stuff in Java. The same is available in Java as well. So the first piece, the timestamp, gives us the timestamp of the element, the timestamp that's been associated with that element. The second will give us the window that that element has been assigned to. And by the way, there are use cases where you actually make use of these values outside of just looking and testing. So you make use of these values within the dofun itself. For example, with time series, which I work with a lot, we make use of that quite heavily. The rest of this dofun is just producing sort of pretty output for us to look at when we are running the tests. So we can ignore the rest of these for now. The pretty print function, just to spend a couple of minutes on one item on here. What we do during this whole process, we are outputting the values. We collect everything into a list. So everything that's being produced by a pipeline, we collect into a list, and then we print it after sorting it. So I just wanted to highlight this because all the output you're going to see is going to look sorted, and everything's going to be done by timestamp. So it's all going to look very, very clean. However, just important to note, it's only because we've manually done this sort to make the output pretty. Normally, it's not going to be sorted and the P collection is unordered. Okay, so with that, let's now go back to our array of values, our values here. And before we run the count again, let's actually just use our get element timestamp and pretty print them. So we run this function against that data, and what we can see is that even though we provided no time information, the create source has associated a timestamp to every single element, which is this rather large negative number, and it's put them into the global window. Now, what the source has done is assigned negative infinity to the timestamp. Negative infinity being defined as within Beam as the beginning of the global window here. And we can actually see that value. So again, in the next cell, we're going to create a global window object, and I output its start and end. And we can see that the value from the start matches the value that we have above, which was what was the source attached to that timestamp. So everything is always within a window. And now let's start manipulating those values and adding different windows to things. So What kind of timestamps could be associated with elements? So obviously sources are free to attach timestamps other than negative infinity. And for unbounded sources like Google Cloud PubSub.io or PubSub or Kafka, there are several options. So with PubSub, the default is if you put an element into the publish and subscribe API's topic, then the time that you put that element in, it becomes the processing time. Becomes the element time. So essentially the processing time is the element time. There are ways of actually passing in metadata about the element itself. So rather than the time when the system sees that element, it becomes the actual time that the data point was created in the real world. We'll come back to these a little bit later. For now, we're going to stick with our batch pipeline. So what I want to do is actually provide more information to that batch pipeline about the time that the stop ticks actually occurred. To do that, I will make use of the timestamp value object, which takes a value of type any and a timestamp of type time. And the way we're going to organize our data, so we have for the $1.05 value at the beginning, we're going to set that to be at 10 o'clock. There are a couple of values that are at 1 second past. And then there is a gap between the value that is at 3 seconds past and 8 seconds past. The next cell, I don't need to go into the details of this one. Essentially, all we're doing is creating timestamp value objects with the characteristics that we've described in this table. And when we output that, we see that, for example, $1.05 for that first element has been assigned to 10 a.m. Now that we've got these timestamp values, let's actually put them into our pipeline and in our batch pipeline and make use of them along with a fixed window. So the fixed window is going to create fixed windows of time at discrete intervals. And the way that our data is going to shape up as it gets tagged into these different windows. So these are, these gray boxes will be the window. So we will have windows, because we're going to create fixed windows of 1 second. We're going to have one value in the first window. There'll be two values in the second window, and so on. In terms of the graphic, the blue are elements and the timestamp for those elements. And we'll use this graphic in a couple of other places as well. So let's go ahead and do that. And we are going to apply our window by using window into function. This will create a fixed window of 1 second. And we are then going to just output the information about the timestamp and which window they've been assigned to in this pipeline. So when we do that, we can actually see our values now have the timestamps that we would expect, and they have been assigned to the windows that we described above. An important part of the Beam model to understand, this can catch folks out, is even though these elements have all been tagged with a timestamp and put into a window, no grouping has been done at this point. So for example, these two values are just independent elements at the moment. They're not grouped together in any way. Because Beam won't do the grouping until we do a group by key or combine function. So this graphic is from the Apache Beam website. And we can see if we replace our create source with Kafka, we're applying our windows. When we are outputting this information, we're still within a Pardue. There's no grouping happening there. Only in the group by key does that grouping function actually happen. Okay, so now that we've got our fixed windows and we've seen what the data looks like, let's run this through an aggregation, which is our count operation. So here we have our fixed window, and now we're going to run it on count per key. And of course, this is now going to do it per key per window. So before, when we did the count, there was going to be 6 elements because that was all the elements in the system. Now there's going to be a count per key. And the output that we see here, and I've gone ahead and tabulated that output to make it a little bit easier to read. This output here is essentially the values that we see up here. So this was our original data set. And we can see that when we're counting, we have got an element coming out of the count operation with the value 1 for the first one, 2 for the second, etc. One piece that's interesting, going back to the actual raw output, is these timestamp values. So the output of the count operation itself is an element, of course, and that will be have a timestamp associated with it outside of the, which is what the count transform is given. And that value is actually here, it's the end of the window. And that's the default value. It's the normal, and it's the one that's is relevant in nearly all use cases. There are occasions in some specific use cases where you may want to change that value not to be the end of the window, but some other point in the window. And there is some capability of doing this by using a timestamp combiner. So in this pipeline, which is a carbon copy of the previous pipeline, with the exception of in the window function, we provided a timestamp combiner, and the value we've chosen is output at earliest. So whereas the default is the end of the window, here we're asking to output at the earliest timestamp seen. To be specific, we are not, this doesn't mean that it's going to output with a timestamp at the beginning of the window. It's going to output with a timestamp of the first element ever seen in that window. And running this with our count and output, we actually see our values have now changed from the end of the window to the timestamp of the first element in the window. And thinking about this, I should have actually maybe made those values a little bit higher than the beginning, so you can actually see that here. But that is the way that you would manipulate those values. Okay, so up to now we've been doing all of this in batch. Let's now move into a more simulating a stream pipeline and see some of the different interesting things that arrive there. So what's the difference between stream and batch here? Well, first of all, in the batch pipeline, we had all of the data available all at once. And as long as we were providing explicit information about the timestamps, they would all end up in the correct windows. We'd get perfect counts all the time. As we know, with unbounded data, the data is going to be continuously arriving. We need to figure out when we should close a window and output a value. We may have data coming out of sequence or data arriving late. Things are going to start getting messy. So how do we do accurate computing and processing of those counts when the data is unbounded? If we look at this graphic in a little bit more detail, just because we're going to use it a little bit later on, the x-axis here is the processing time. So when our system is aware of data coming, has been made aware of an element being processed, and these are all the elements flowing through the system. The values within the elements, so when they are seen in the real world here, for these three elements that we have highlighted, was 8 a.m. So these two arrived roughly around, when we get to see them, was around the same time as when they were created. This particular one arrives much later. And examples of this would be, a mobile application that's sending clickstream, it loses connectivity, and when it comes back online, it sends the data. So now we've got this idea of late data arriving, out of order data. How does the system know when to output and how to deal with these things? So the way that Beam does that is with the watermarks, and just a little bit more intuition on that. In this graph, the event time, in other words, when something happened in the real world, is on the x-axis. On the y-axis is the processing time when we get to see the thing. If we were, if as an event happened, we immediately saw it in our processing system, we would get into this ideal line situation here. So, of course, that never happens in any real system. There's always a lag between when this thing happens in the real world and we get to process it. And of course, more importantly, that lag is never consistent. So it's going to increase and decrease based on various things like machines falling behind, machines falling over, etc. And this essentially is roughly the watermark. And one of the technical leads early on taught me this intuition, which I think is very useful, is a watermark is our estimation of the data that we'll see into the future. Essentially with Beam, what it does is going to have this notion of tracking the data, and once it's certain that it's got all the data within that it's expecting to arrive in a certain window, it's going to output a value. The watermark itself, a pipeline has different stages, and each stage can have its own watermark. Once the data is in the pipeline, we can actually track the watermark perfectly, because different stages within the pipeline, and we'll come to a graphic in a moment that will help with this, different stages in the pipeline will know all of the data that is in the system as a whole and will know where they've got to. However, for our sources, these are always going to be an estimation. We estimate the watermark on our sources. In terms of what does it mean to have different watermarks in different parts of the pipeline. So let's imagine we have a pipeline where we're reading from two unbounded sources and we are carrying out various transforms. Each one of these transforms can have its own watermark, input watermark and output watermark. For this side, the A is an unbounded source, and we're going to estimate the watermark there. C will be its watermark is going to its input watermark is going to be the output watermark from A. E is output watermark is going to be the oldest of the ones from C and D. And of course, it's the oldest because if either of any of the stages upstream of it are at a certain watermark, E can't progress until the watermark is progressed upstream of it. Now, to actually simulate some of this stuff in our code, we're going to make use of another utility class, which is the TestStream class. Now, with TestStream, so we're going to create a TestStream object here. What TestStream allows us to do is allows us to very precisely model a data arriving and moving of the watermark manually so that we can get a consistent stream to run all our experiments through. The way we use it is we create the TestStream object, and at this point, we're going to advance the watermark on the TestStream to 10 a.m. We then insert a value. And please note, I've deliberately not inserted a timestamp value. I've actually just inserted a raw value without any time information. So at this point, other than where it's been inserted into the stream, Beam won't have any a notion of the event time for this particular piece. It's just going to use the time that it was inserted into the stream. So at 10 o'clock, we have this one, and we move the watermark by 1 second. We apply our other elements, and so on until the end. Finally, the test stream, we need to close it off by advancing the watermark to infinity. Okay, with the test stream object, so now we're going to use that within our pipeline. So we're going to use our test stream. One thing about test stream, you can't keep reusing it. You have to create a new test stream because it will exhaust it when you run it through the pipeline. Just something that that'll catch folks out. So we're going to use the test stream and we are going to run our fixed window against it. And we're going to do our get element timestamp to look at the timestamps that's been associated with the values. Here we can actually see, and we'll go to the table, which is just shows these values a little bit easier. We see that the actual table is an exact match for the data that we had previously around event time. So it looks like it's done a perfect thing. Well, the reason for that is we have been very, very careful in creating the test stream to make it perfect. We didn't put any data out of order. We moved the watermark carefully as we inserted elements. Therefore, the processing time will be matched exactly the event time in this case. Of course, real systems don't do that. Real unbounded sources aren't going to be like that. It's going to be out of order and late data. And to just to finish this before we add some variance into that test stream, I do for this same test stream that we had above, we do the count operation. So now I'm going to count and output our results. As we would expect, because we've carefully crafted this test stream, the results are as before and everything is looking okay. Right, so let's now put in some real world problems into our test stream. What we're going to do, similar to the graphic that we saw before, where there was some late data, we're going to introduce late data into the test stream. This was our previous data set, and what we're going to do is insert a new data element, which is corresponding to 10 o'clock dead, and add that after 8 seconds into our test stream. So here, everything in this code is the same as the cell above, with the exception of this final line, where we've added this $1.09 value as late data that arriving after the watermark has been moved to 8 seconds. Okay, what we're going to do is a count and get element timestamp. When you run this, we're going to get these results, which I have represented in this table here. And we now notice that we have this incorrect value. the count at that final window has now moved to 2 instead of being 1. So that value has gone and ended up in the wrong window. And that's not surprising because we didn't give the system any other information other than the processing time. So this is what the system saw. It saw this late data come in into the final window, and it's applied the count there. How do we actually get it to more correctly do our processing for us? Well, based off what we've seen before in the create event, we need to give it event time. And by the way, so for sources like PubSub and things like Kafka, as well as the processing time, as we mentioned earlier, you can provide event time. So with PubSub.io, this is through the timestamp ID value. Essentially, this is metadata that you can give to PubSub, and PubSub will then pass that metadata on to your pipeline when you use that ID value. In order to simulate this in our test stream, we're going to make use of timestamp value again. So in our timestamp test stream, we have as before, we're advancing the watermark and we are adding elements. But in this instance, we are going to add timestamp value elements to this stream. And we're going to provide a timestamp of start, which is the same up here. And we're going to also increment the timestamp as we move these value forward. Finally, for our late data item, we are also including the start time. So our late data item is now being added at the end of this test stream, but the timestamp value is the correct timestamp for that element. So if we were to run this against our get element timestamp to introspect the information, we can now see that we have a new value added, which is this $1.09, and it's got the correct window associated with it and the correct timestamp. Okay, so let's run this through our count. So let's do an aggregation now. So this data exists here. We're going to do a fixed window of 1 second. We're going to do our per key as per normal, and look at the output. So again, this is the output. I've made it nicely in this table here. We can see that the value at 8, that window between 8 and just before 8 is correct. It's no longer 2, so that late data element is not there. But we have this late data element value here. However, the count for the window at the beginning is still only 1, not 2. Now, why is that? Well, the default for Beam is to drop late data. So if the watermark has passed and the fixed window has emitted the pane of information, the default is to drop late data and not include it in and not output in any further computations, which may be the right thing that you would need for your business use case, or you may actually need that value. So even though it's coming in late, you want to see it downstream. So how do we do that? Well, we can actually change the window into function and allow lateness gives us the time to allow after the window closes where data is still going to be processed by the system. In this case, 10 seconds. So that would mean any data that comes in after 10 seconds after that window closes is going to be processed in event time. Anything after 10 seconds will still be treated as part of the default, and that data will be dropped. So now when we run this count pipeline, we can see that we have this new entry added, which is again at 10, and it contains 1 element. So in this table, we have that first element that was added. The late data element is also being output now. Now this may, again, cover the use case where you're now seeing this late data also downstream. However, sometimes we don't just want to see the late data. We want to have output which is correct based on the total count for the elements that would have been within that window, for example, if they hadn't arrived late. So if we think about it, there are, actually, I'll go back quickly. So the value here, that is that late data, we actually want to include it in this window and include it in the count. So that count to become 2. So why didn't Dataflow do that automatically for us? Beam didn't do that automatically for us here. And to explain that, we need to introduce one new thing, which is panes. And I really should have had a graphic here to explain panes, but essentially, for every window, a window can output one or more panes of from the window. Up until now, we've mostly been seeing on-time panes. So there are three types of panes that can come out. So after the watermark trigger is fired, we've been seeing the values come out. This final value that we see here is actually the late pane. So this is instead of on time, there is a pane of information that's come out the window, which is late. So, and there is also one other type of pane, which is early, which we'll come to in a moment. But essentially, when a pane of information comes out of a window, there is two things that you can do with the data within that window. So once you've emitted the pane, you can choose to discard all the data that's in that window, or you can choose to keep it. The way that we describe that is discarding panes or accumulating. The default is to discard. So this is the reason why we had a value 1 here, but our count when the new late data item came was still only 1 instead of 2, because when the first pane came out, it was the values in that window have been discarded. In this final one, they have been, so we have a count of just 1. In order to change its behavior, we can use accumulating panes. So here, we are going to add an accumulation mode to our code. Everything else is as before, fixed window of 1, allowed lateness 10, and we're going to change this to accumulating mode. Now, when we run this, the other thing I'm going to do is change the way that we print information. Up until now, print pane info has been set to false for our get element timestamp class, our do font, sorry, and now we've set it to true. We can actually see some extra information that was always available for these elements. Again, I'm going to refer to this table rather than the raw data. Here we can see that with the pane information, we're getting a first and last, whether it's the first pane in the window, whether it's the last pane in the window, and the timing. So all of these are on time, aside from this late pane, which now is set to the value 2. And this is because we are accumulating now instead of discarding, and we have the correct value. Please ignore this value, which is showing up here. We are using the direct runner here, and the direct runner Python triggering implementation stuff has got some known issues, and I actually talked to Pablo this morning about it, and we can. They are working on hopefully fixing this. So hopefully in the later versions of the notebook, this won't be there. But for now, please just ignore this data point that's coming out. Essentially, this is the same data point from previously being output again, which it shouldn't do. I won't actually go through this graphic. After looking at it a bit, I don't think it does a great job of explaining anything. So we'll skip that. So up until now, we've been dealing with on-time panes of information at the watermark. We've been dealing with late data. I mentioned there was another pane of information early. And to explore that, we're now going to get to triggers. In terms of triggers, to be able to show some of the trigger characteristics, we're going to make a little bit of a change to our code. And instead of a 1 second fixed window, we're going to use a 5 second fixed window. This gives us more elements in the window to play with. So the characteristics now change. So there's 5 elements in the window, which will start at 0 and end just before 5 seconds. And we can ignore the second window here. With this, I'm going to just, sorry, I'm just going to have a little bit of water. Okay. So in this next piece, I'm actually going to use a trigger. So we have our fixed window of 5 seconds, and we have a new piece, which is a trigger after the watermark. Now, the after watermark trigger is actually the trigger we've been using throughout this process. So I'm just showing it here to show the syntax, and the output of this will be exactly the same as if I don't have the trigger here at all, because the after watermark and the discarding and the allowed lateness of 0 is the default position. The output of this, as you would expect for the count operation, is that there's a count of 5. The pane info is also all on time, so we have 5, and we have that 1 element in that final window. So this is pretty much as before, and this has all been using the event time trigger. So after watermark is an event time trigger. The other type of triggers that we can make use of, one of them is data-driven. And here, if you imagine if you had a 12-hour window that you set up in a fixed window that's trying to count the number of activity that's going on with a machine, we may not want to wait 12 hours before we see that that machine suddenly had 500% more load than it normally would. We may want speculative results to come out the window. So we know they're not correct because the window hasn't closed, but we still want to see these results because we want to have a lower latency access to the information. If there's been a spike in load, then we can do something about it downstream. Now, how do we do that? We do that with, one way we can do that is with a data-driven trigger. The one we're going to use is after count. Now, what this does is rather than waiting on watermark, it's going to count at least n elements. If at least n elements arrive into the window, it's going to fire. I'm making sure to highlight at the at least point. So it's not going to be exact. So if we set this to 2, it won't fire exactly when there is 2. It will fire when there's 2 or more. So it could be, if we go back up to our thing here, that because 2 arrived in this second window, it can either fire with the value 2 because it sees these, or it could fire with the value 3. And so this is slightly non-deterministic. With the test stream, it's always going to produce, I think, the same results. But just be aware of that non-determinism when you use a data-driven trigger. The way that we put the syntax together, so there's a very nice thing with the Python after watermark trigger. You can compose other triggers directly with it. So in this case, using the early E, we can provide an after count of 3. So in other words, when there is 3 or more values that have entered the window, output a result. If we recall from before, when we didn't have this secondary trigger, we had a value of 5 and 1 output in the table. When we run this now, we're going to have a value of 3, 5, and 1. So this 3, the pain information for that is early. In other words, this is a speculative result that is the result of after count triggering. If we look at this graphic here, we can see this a little bit more easily. So the after count trigger fired when there was 3 elements in the window, and we are not discarding, so we're accumulating. And then the watermark trigger fired at the end of the window, and the value was 5. And then the final one is for the final window there. So data-driven triggers are one type of trigger. Another type of trigger is processing time triggers. So processing time triggers are basically based on the wall clock. And a good example of this would be in our use case where we had like 12 hours and we're waiting for values. We can actually output a value every minute or every half hour if we wanted to, based on the actual processing time. And you can also then compose multiple triggers together. So in this particular case, we're making use of a trigger called after any. Oh, didn't mean to do that. Didn't mean to do that. Sorry. So the after any will fire when any of the sub triggers within it can fire. So here we have after any, and we've included 2 different triggers. So after processing time, so every 3 seconds, we're going to output from our window. Given our window is 5 seconds, that means it's only going to do it once anyway. And the after count. So if either of these triggers conditions are satisfied, it will trigger. And of course, at the end, we're going to have the after watermark. Now, when we run this result, please note there is, as I said, with the direct runner and the Python trigger stuff, there are some issues. The processing time one is not firing. So here we're seeing the value 3 from the after count. We see the value 2 from the watermark. The reason it's 2 and not 5 is because we're using discarding in this use case, and 1. There should be one more line here, which is the processing time. Again, we've got to raise a JIRA on that. This is a direct runner issue, we believe, and if you're running with Dataflow Runner or Flink Runner, then you shouldn't see that. You should actually see the correct results. How are we doing for time? Okay, I think we've got enough time to cover the next couple of pieces. So another thing that people often do with data or processing time triggers is when they're interacting with the global window. So one of the properties of the global window that we saw very early on in this use case was the global window is end is set to positive infinity in terms of what beam knows of time. And therefore, in a streaming world, if you put anything into the global window, and do something like an aggregation or a combined key, nothing will ever come out. And the reason for that is the watermark's never going to trigger because we're never going to get to infinity. If you then like shut down the pipeline with sort of a drain operation, etc., then you might get to infinity. But in normal operation, nothing is going to come out of that pipeline. There are use cases where you may want to make use of a global window. A very good one, I know Ken is doing a talk later on state and timer API, is where you need data to persist across a large length of time in the state API itself. And so you might want to put data into the global window because of those that case. There are other use cases as well, for example, with a slowly updating side input, which makes use of the global window. So how do we get information out of the global window? Well, as I said, the trick here is that rather than using the watermark trigger, we need to make use of either processing time triggers or a data-driven trigger, which will then fire as data is coming in. In this case, we've reused the trigger that we used before. And when we run this, we're getting the output we see below. One thing I just wanted to highlight on this output is, of course, the timestamp that's associated now with these values as we're getting them output is is the end of the global window. So be aware of that as you're doing this. There are ways around this. So when you're working with state and timer API, which Ken will talk about in the session, two or three sessions after this one, the timer API, when that fires, it will associate the right timestamp to things, and then you can do another windowing afterwards. I won't go into the details here, but there are ways around this. Just be aware that by default, the global window, the timestamp that you see here is going to be the one that's attached. Another important thing about the global window, what's coming out, because it's data-driven or processing time-driven, there's going to be no order, right? So it's completely random order what will come out of that window based off the data going into it. So with triggers, we are able to choose completeness, so making sure we have all of the data before we do an output. We can go for latency, so lower latency by outputting data just based on the count of number of elements going in or processing time, or we can do it based off of cost. So one thing, when we were talking about accumulating mode, in accumulating mode, if you choose accumulating mode, accumulating rather than discarding, and you have a low latency trigger, then imagine you've got a window that's 1 hour long and you've got a couple of 100,000 QPS or 10,000 QPS. Let's keep 10,000. You have 10,000 QPS. Every time elements coming in, you're firing elements but keeping everything there. So the amount of data coming out is going to, I believe, it's gets n squared, right? So you're doing a lot more processing for that, and that's one of the cost considerations that you have control about. You can either use you could use discarding in that example for so that you are not continuously increasing the volume of data that you're having to process based off a small amount of data coming in, or not small, but a reasonable amount of data coming in. The final piece, and I think we have enough time to cover this, is around merging windows. So for merging windows, this is based off, this is a data-driven window, and events coming from, so for this particular use case, we need to change the test data a little bit. In our test stream, rather than using our stock data, I'm going to use clickstream data. So with the session window, which is a merging window, we've got, we're going to pretend that we've got a application where I, as a user, have done some browsing and made a purchase, and then later on I've gone in and done some administration. So this is the test stream that we've created: browse, purchase, based off of these times, and then I'm doing some administration. With the session window, what it does is it will allow us to output based on the gap between the data. So what we've done is beam window sessions, 9 seconds. I should have probably put an hour here. I'm sorry about that. But essentially, what this will do is it's going to wait to see if there's a gap in the data coming in for a particular session, for a particular key. If there is a gap of 9 seconds, then it's going to output the results. So what this allows us to do with this data set that we have, and I've given a key of ID1, is because these 3 events were close together, and then there is a 9-second gap, the output of this is going to be 2 separate sessions. So in other words, it's done the sessionization for us for the clickstream. I was on doing a browsing and then I made a purchase. That becomes 1 session. I later on then did some administration. That becomes another session. So when we run this, we get these 2 values that are output from the session window. Okay, and with that, we've come to the end of this piece. We can move on to questions and stuff if there are any. If you want to bring back everyone on screen, I guess, right now.
Okay, thanks so much, Reza. Give us a second. Okay, we're good. Actually, most of the questions have been answered by Ahmed while you were leading the session. Ahmed, I don't know if there's any unanswered questions or something that you want to raise.
No, I think I answered all the questions on Slack. But we didn't receive that many questions, I would say, handful. So if anybody has any questions, I think this is probably a great time to ask questions.
One of the, let me see. I believe most, yeah, I think that all the ones that were made on the Slack were covered. Let me see if there's any like recurrent one, but I don't think there's any recurrent one. I mean, we received lots of comments and thanks about the notebook and how complete it is. Thank you so much for putting the time into detailing it. We have a question from Pierre Oberholzer on the YouTube chat. Where is the state persisted if you need to keep accumulating your results over the entire global window? Is it on memory or disk, or is that configurable?
It is actually, it depends on the way you are running the streaming mode. So in the direct runner, it will be all in memory. But I don't think that's the most interesting one, because people usually ask this when they are trying to run a real production pipeline. And when they are really running a production pipeline, so if you look at data flow documentation, there are 2 ways of we are doing streaming. We have something called so-called streaming appliance, and we have this newer technology called streaming engine. And in the first one, the state is stored on disks, and you will be responsible for not accumulating things forever. Otherwise, things will eventually be too much. In the streaming engine version, which is our newest version, which we have essentially a different service that is running behind Google services for data flow to keep track of the state. If this is a question about how Flink and Spark, etc., does, that is an area that I don't have enough information, but I will guess that it will essentially be done mostly by storing things on disk. But I think this question is getting to the production experience. I can talk more about data flow. It will be hard for me to say much about Flink and Spark.
Okay, thank you, Matt. We have another question by Ross Young asking, is there an equivalent test stream object for Java?
Yes.
Yes.
Okay. And then comments by Audrey Lorberfeld, who has been following all the Beam College sessions, just thanking you for how clear the walkthrough was and at the right rhythm and everything.
Thank you. Thank you for your time.
So let me see. I don't think we have anything else.
There are 2 more questions on Slack, just I think came after we start answering. One of them is from Pradeep about,
oh yes,
yeah, how can we debug if in case something wrong in streaming mode? Again, like if this is about direct runner, like test stream is a great idea, logs are a great idea, but if it's a production thing, we have a whole suite of tools to kind of look and understand this. It might eventually devolve into looking into logs and those tools. It is clearly hard to debug a thing that's running in streaming in production. There are a series of tools. I don't think you will be able to cover everything here. But like the best suggestion would be start with Direct Runner, start with Test Stream. Make sure whatever you are running is like solid before running on production data. And another question from Tudor: how can we test pipeline behavior as close as possible to data flow? Yeah, I don't think I will be able to give a satisfying answer short of you have to run some tests on data flow. As much as we try hard for like keeping all these runners behaving in similar ways as much as possible, it's not 100% the reality. So if you really want to test something, you actually need to run on data flow. But you can run things with obviously smaller data. You don't need to start with all your data on data flow. And the direct runner should probably get you like 95% to your end goal before you spend anything on data flow.
We have one more question from Tudor. How can we test the... Oh, yeah, that's what you just answered. Sorry. Okay, I think that's it.
Thank you, everyone, for attending, and please do provide feedback. This was the first time we tried this particular style for the delivery of this, and so all feedback very gratefully received.
Thank you. We'll let you go to get some sleep, Reza.
Thank you. Thank you, Ahmed. Cheers. Bye.
Thank you, Ahmed. Bye. So we'll continue the next session in 8 minutes. And the next session is actually... the next session is DoFN lifecycle and user code requirements. You have the slides available, and there's also a notebook for the code walkthrough. And we'll start that in 8 minutes. Feel free to stay here, go grab some water, answer those pending emails, and we'll see you in a bit.
Hi, welcome again. Now we have with us Israel Erraiz with our next session. Well, first of all, Israel is a strategic engineer at Cloud and Google, based in Spain. He has worked in different data science roles at BBVA. I don't know how to pronounce that in English, sorry. Data Analytics and Amadeus. He holds a PhD in computer science from Universidad Rey Juan Carlos and has been a visiting researcher at universities in Europe, Canada, and the USA. So, welcome, Israel. He today is going to give us an introduction to Pardue and Friends, methods of DoFN to control its life cycle. And well, this is going to be more like a workshop. This is a 60-minute session. And well, I let Israel to explain what he is going to be doing today for us. Thank you, Israel. Welcome.
Thank you. Thanks for the introduction and for the opportunity of speaking here. So yes, so I'm gonna be showing some slides first about Pardue and DoFunctions. So, and if you don't know what's that, don't worry. So we will see like shortly. And then after a few slides, we are gonna actually do exercises hands-on using a notebook in Google Colab to showcase how Pardue and DoFunctions work. Okay, so every time we have to do a map, an operation that is applied element by element in Apache Beam. So that's what the Pardue makes. But the Pardue is actually much more than that. So a Pardue has side inputs. A Pardue has a lot of other options that makes it a very powerful tool. But we will not always need to use all these options. So if we have to do a map in Apache Beam, so we don't have to do necessarily a Pardue. So there are some helper higher level functions that we can use, such as a filter or map elements or map or flat map elements that are kind of like higher level Pardues that we can just apply on our data. And the first exercises that we're going to be seeing today are actually about this. So what's a Pardue and a DoFunction? In Apache Beam, data is processed in bundles. Okay, so we have our data here, like for instance, a file, like a full file. And then when we are processing the data, Beam is splitting the data in chunks in what we call bundles. And each one of these bundles is going to be processed in parallel in different workers. Okay, so if we are doing a DoFunction, if we are doing a Pardue, we have to apply a DoFunction. If we are doing a map, so each map will be actually applied to just one bundle. Okay, or maybe more than one bundle, but each bundle will be processed in parallel in different DoFunctions. And each one of the DoFunctions is going to be actually executed in different workers. That will be one process per worker typically. This is depending on the details of the runner for sure. Okay, so different runners will execute this differently. Like for instance, in a batch runner, the bundles will typically be larger. In a streaming runner, will probably be smaller. So, and each one of these workers, each one of these processes of a function, typically, for instance, in Dataflow, will be a different process in a machine. So if we have a machine with several CPUs, so we will have one process per CPU. So if we want to write like a more detailed Pardue, so we have to write a DoFunction, and to write the DoFunction, we have to overload some methods of the DoFunction. So here we see all these methods in Python snippet. Okay, so this is similar in Java and other languages, showing just let's say for illustration purposes here in Python. So the main method of a DoFunctions is this one, process. So here we process each one of the elements. So we receive as input one element, and we do something with that element. We transform it into a different format. We may filter it. We may expand it and then produce several outputs for one element, like in a flat map, and so on. When we start processing one bundle, the runner will actually call this start bundle method. So if we need to do some initialization before we have to process one file, one element or one bundle, so we can do it here. And similarly, finish bundle will be called by the runner when the bundle finishes. So this typically is going to happen several times per run per job, okay? Because we will be processing several bundles. And when the worker starts, so the runner will call this method setup, and when the worker finishes, we'll call this method teardown, okay? And typically this will happen once, okay? Because well, so the worker will be created, and when it's not needed anymore, if the runner destroys the worker, like for instance we get auto scaling or any other situation, so it will be destroyed, and this method is called. Okay. Let's see how these methods work. Okay, so this is the life cycle of a do function, and this is a very powerful workflow that we can use to make very complex part do's. Okay, so when the worker starts, the first thing that our runner is gonna do is calling this method. Okay, so this is a good place if we have to start, I don't know, for instance, a database connection, if we are gonna use this database connection when we are running and processing our elements. Then for every bundle of data, the start bundle is called, okay? And then for in the bundle, we will have typically several elements, and then for each one of the elements, the process element is called, okay? And we will see later, or you will see later, about the state and timers, the state and timers API. So we have some stateful transformation. So this is where we are reading these state objects, this method in the process element method, okay? The process element method is going to be called several times, like for once per element, and then the start and finish bundle are going to be called, well, also several times, but typically an order of magnitude less, because so this is called once per bundle, okay? And then typically if we are dealing with a state, as you will see later, so this is where we write the state objects in finish bundle. And then when the worker finishes, so we call teardown. So if we created a connection in the setup method, so this is the place where we should close that connection in the teardown, okay? Well, the worker is going to be probably destroyed anyways. Like if this is running in Dataflow, the worker will be a virtual machine that will be destroyed. So it's really not such a big deal if we don't remove some of the connections, but let's say if we want to maintain things clean and decent, so we should actually close all the connections here. Okay. So today in the exercise, we're gonna actually train this flow, and we're gonna see how it works with an actual live example. So the different methods of the do function. So typically we will be using the process method only, no, in most of the situations, because that's where the transformation happens, for sure. But in some situations, so it will be very handy using other methods like the setup, start bundle, finish bundle, and so on. Okay, so remember, setup is a good place to start like a connection to a database, or open any other kind of connection, or start any other helper process, okay? Here, if you're gonna be performing side effects that you will need to clean up later, okay? Like creating temporary files, modifying anything externally to the worker or to the process, this is not a good place to do this, okay? So let's say resist the temptation to do this here. The start bundle, if you, for some reason you need to keep track of the elements that you are processing in a batch, and then again in the state and timers presentation, you will see some situations in which this is a good alternative, like processing the elements in batch, like for instance when you're calling an external service and do some batching calls. So here is where you have to start tracking this batch, okay? And then in finish bundle is where we should actually clear the state, okay? In finish bundle, you should, for instance, do the call to the external service, return the result, and then remove the batch and proceed to process the next batch of data. And then in teardown, again, so anything that you opened here, you should close it here, okay? So like any connection, any database connection, network connection, any process that you started, so you should actually stop it here, okay? And then make sure that, let's say, that you clean after yourself, okay? Because the worker is gonna be destroyed, and then you are not gonna have any other opportunity to do this cleaning after this, okay? So you shouldn't, let's say, leave anything behind, okay? Good. This may sound a little bit abstract so far, okay? So don't worry too much about that, because when we see the examples, this is going to be a little bit more clear. One last thing before we move on to the exercise, one, let's say, word of warning about thread compatibility, okay? The do function should be thread compatible. When you're working in Apache Beam, so you're going to be running your code in a distributed system. The processing is going to be parallelized, let's say, for you, but you should resist the temptation to do some parallelization yourself, okay? In particular, if you're writing a do function, think in sequential. So you have this P collection, which is it's a, let's say, potentially infinite collection of elements. Treat it as a sequential collection, okay? And process elements in a sequence, because your do function process, especially if your worker has several CPUs, are going to be executed as several processes in the same machine, okay? So don't try to start like any parallel thread or try to access any common resource from several instances of your code at the same time or anything like this, okay? Because the SDK is not going to be thread safe in a general situation, okay? So if you create your own threads, if you do your own parallelization in a way, you have to take care of it, okay? And this is very difficult to do in a distributed system that is running your code in lots of parallel workers, okay? So this is a recipe for disaster if you try to do this, okay? So resist this temptation, think in sequential, and let Apache Beam parallelize for yourself, because that's actually, let's say, the purpose of Apache Beam. Okay. So this is all about the slides, okay? I don't have a lot of more slides because all this, everything that we have seen here, we will see it better in an exercise. So we are gonna move on to a hands-on session with a notebook in Google Colab. If you want to follow the session, the notebooks are uploaded to the GitHub repository, day 2. So you should see there the notebooks. There's one notebook that's blank, so we can actually write the exercises in it. And there's another one with the solutions. Please don't have a look at the solutions just yet, okay? So take the opportunity to try to do this by yourself and learn rather than just look at the solutions. Okay, so if you want to follow the code that I'm gonna be writing, so please use this link here for the notebook, make a copy, and so you can follow the same exercises that I'm gonna be making. Okay, you can also take the notebooks from the GitHub repository and run them in local if you prefer. Okay, but if you prefer to use Google Colab just with a browser, so just use that. Okay, so I'm gonna stop the presentation here, and actually I have Google Colab open here, and I need to reconnect because I've been talking too much. Let me just put this a little bit bigger. Okay, so I hope that's good enough to actually be able to read in the screen, and we are gonna start with the exercise. So this is a notebook interface. I hope you are familiar with it. So here we can have code and text living in the same document, okay? And this is a document that we can execute, okay? That we can run, okay? So the first thing that I'm gonna be making is installing Apache Beam in this notebook. The notebook comes with a Python environment, and we can actually install packages here because this is a virtual machine that is connected to the internet. Okay, so this is installed already. Maybe in your case, if you run the notebook for the first time, this step is gonna take a little bit more of time, and you might see some errors here sometimes, like in the messages. Those are just, let's say, warning messages rather than errors, so you may ignore them, okay? So run the next cell, okay? And if you can actually run this cell and it doesn't fail, then you are all set to do the rest of the exercise, okay? So here, I'm not writing this code, so I'm just, let's say, copy pasting the code from the solution because, well, so it's a little bit boring to import everything. But what I'm doing here is just importing Apache Beam to use Beam in the rest of the code. And then we're gonna be using the interactive runner, okay? And then we are gonna be using this object IV to have a look at the contents of a P collection while we go with the exercises, okay? and then the date time, because we're going to be using some dates and times later on in one of the exercises. Okay, so if you have managed to run this tool successfully and it didn't fail, then you are all set to do the rest of the exercise. Let's do the first exercise, okay? And here I need to, let me fix this now, okay? Okay, I did something wrong. Let me just remove this. Okay, now this looks better. Okay, so this is the first thing we're gonna be making. So we are gonna have a pipeline in Apache Beam, small pipeline, that's gonna take some numbers, here are numbers from 1 to 5, and we're gonna execute it by 10, all the numbers, and we're gonna produce numbers like 10, 20, 30, 40, and 50. This is a Pardue, okay? But this is a very simple application, not a very simple map, okay? We don't necessarily have to write a full feature do function just to do this, okay? So we're gonna see how to do this with a Pardue and how to do this in a simpler way by using a higher level Pardue frame, okay? Like a map in this case. So let's start with the solution with the do function. When we have to apply a do function, we have to create a class that, in this case, this multiply by 10 do function that inherits from being do function, okay? And then when we are inheriting from being do function, we are forced to actually override one of the methods of a do function. And this is the process method, okay? So we need to declare a method that is called process and that it has actually this signature. Well, it's a member of the class, so it needs the self member first, and then it receives as input the element that is passed to. Oh, okay, I cannot save it. Okay, well, I will save it later. I will make a copy and I will save it later. Okay, so this is the element that will be received by our do function. Okay, so this is the 1, the 2, the 3, the 4, and the 5 that will be received by our do function. And here we need to do the transformations. Okay, the transformation that we're gonna be making, it's well, so the output is gonna be the element multiplied by 10. Okay. Well, clear, so easy. This is an easy task. And now we need to return the element or the output as the result of the process method. But we cannot do just a return output, okay? This works as a generator, the do function, okay? So this is gonna fail because this is not a generator. So we actually need to use GIL here, okay? And this will work, okay? So here with GIL, the signature of this method will be something that we can iterate as output, okay, rather than just one element, okay, because we are doing the GIL, so we can iterate over the output, okay. If we return only one element, so this would fail, okay. Sometimes people do things like this, okay, to return something that is iterable, but it's kind of a dirty trick, okay. I don't like it, so let's use actually GIL, okay. Easy, okay, so this is actually the do function. Let's actually now write the pipeline, okay? So we have already initialized the pipeline with some options. In this case, we're gonna be using the interactive runner, okay? In order to be able to have a look at the peak collections as we go. As a generic comment, we cannot inspect what's inside the peak collection in our pipeline, okay? So, for instance, if we had here as the constructor, in the constructor of this class, one parameter that we need to pass, so we couldn't take that parameter from inside the peak collection, from the data. That should be available externally to the peak collection, externally to the pipeline, for instance, as a command line input argument that we use, okay? So we cannot, let's say, just take things from a peak collection. But the interactive runner allows us actually to have a look about to what's inside of a peak collection. Okay, so for instance, we are gonna create the input data. Okay, for that I'm gonna use the pipeline itself as the first step, and then the pipe operator that concatenates two steps in a pipeline. Okay, And we are gonna create a synthetic collection of data, okay, with the numbers 1 to 5. Okay, well, I could have used like a range here or whatever, but let's just type it. Let's have a look at this. Okay, with the interactive runner, I can do something like this. Okay, and if I run this and this is correct, let's see. I will see here the input. See, so this is the input that I just created. Okay. It has only 5 elements, and these are the values, the numbers 1 to 5. Okay, so good. So this is working. This is what the interactive runner provides. Okay, and I strongly recommend you running things in an interactive runner when you are designing your own pipelines, because it will make things much easier, because you have visibility about what's going on with your pipeline. Okay, and if you're not using the interactive runner, that might be more difficult to have that visibility. Okay, good. So let me just remove this. And let's actually now have a try to produce an output. For the output, the input element is gonna be the peak collection that we just created, and here we are gonna actually do a Pardue. Okay, and to make a Pardue, we need to instantiate the class that we just defined. Okay, so this multiply by 10 do function. Okay, and then let me have a look at the output. Let's see if it works. So if it works, see, we see here the numbers 10, 20, 30, 40, 50. What has happened? So each one of these input elements was passed to this process method, put in this variable, okay? And then so we return this element here, which is the multiplication by 10, okay? So it has worked as expected, okay? Let me just show you very quickly that if I do something like this, a return instead of a yield, so this will fail, okay? Let's see. I hope it fails. And it, okay, see, because an int, the number that I'm returning, is not iterable, okay? Sure. Okay, some people do this, things like this, sorry, like put this around a list or about any kind of iterable structure, okay? But the correct way is actually using yield, okay? Okay. Let's see if it runs. Okay, clear. A lot of code just to multiply by 10. So here we have to do the process. We need to remember the signature of the method, make sure that we override the right method. We have had to use inheritance for this. Oh, this yield thing can be a pain if you forget and you don't realize. And then this is just like a lot of code just to multiply by 10. Can this be simpler? It can actually, okay? So it can actually be simpler, and we're gonna see that as the next exercise, okay? So a do function is a very powerful thing, but most of the times you are not gonna need it, okay? Like this time we're just multiplying by 10, okay? So we don't have to do all this hassle just to multiply by 10, okay? So let's actually have a look at the next exercise, okay? So the next exercise is exactly the same one, okay? So I have here some code. It's the same code that we just wrote, okay? I don't want to write it twice, okay? But now we are gonna be making this example a little bit simpler, okay? So here we're gonna be using one of the Pardue friends, okay? And then the output is gonna be like before, input, the pipe operator, and now instead of using Pardue, let's see, well, there's a lot of functions here that I can use, and one of these is the map, see, map, and there's also a flat map, and there's a filter, okay, and there's a map elements, or that was, okay, I cannot find it right now. Well, I cannot find it, yes, I cannot find it because map elements is actually when I have tuples as input, and I don't have that, okay, so well. And then the map is applied to the elements, okay? And now here, as the function, I can use just a lambda, okay? So I can use just a lambda function, okay? Where I take a number, and then I multiply the number by 10. This is much more Pythonic, okay? And then if I have a look here at the output, well, so the output should be the same, hopefully. Let's see, okay, good. Great, and in the same way, just let me just copy this, comment this, and show a couple of examples. In the same way that I'm using map here, I could use, I don't know, like filter, okay? I'm gonna filter the numbers, and I'm gonna keep only which are those that are even, okay? That can be divided by 2, okay? So I'm here applying a lambda that takes as input the number and produces as output a Boolean, a true or false value, okay? When this is true, we're gonna keep the numbers. When this is false, we're gonna drop the numbers, okay? Okay, let's see here. See, we are just kept just the even numbers. I'd let you as an exercise to implement this in your undo function, okay? So how would you implement this in your undo function? Okay, so that's actually that's really not difficult with what we have seen so far. Okay, so share your code in Slack, for instance, where in order to like if you want to have some feedback about that. And just let me see, because someone mentioned me in Slack, and I hope that the okay, yes, we are live with myself. Yes, we are live. Okay, so maybe I don't have a lot of feedback here, so maybe the show wasn't running. Okay, so in addition to map, so here you have a lot of other functions. In the slides, you have the details of the most frequent ones, and I encourage you to use those to simplify your code rather than writing your undo function just to do simple things. Okay, so here we don't have to create any other class. We just do a lambda, which is a much more natural way of doing things with Python. Good. Great. So then, what's the usage of a do function? Well, there are many, okay, but it's the complex use cases. Okay, so let's see how the function works by exploring the rest of the methods that we haven't used so far. Okay, and for this, I'm gonna move to the next exercise. Okay, just let me collapse this here, and we are gonna do a slightly more complex exercise. So we are gonna, so here I'm already creating a pipeline, okay? We have some text here, and we are gonna be playing with this text, okay? For this text, I have already created here some code, okay? For, let's say, for simplicity. Just let me run it and see how it works. These are the first lines of the Don Quixote de la Mancha. Here we are creating a collection with these lines, okay, which is one of these elements in a line, okay. And this will be the first element, this will be the second element, this will be the third and the fourth element, okay. And these are this has only 4 elements, okay. But these are full lines and very long lines, okay. And we want to work in this example with words, with isolated words, okay. For that, we are splitting each one of the strings by spaces, okay. And then the output of this function will be a list, okay. And when we apply a flat map, for each one of the elements of this list, we will have an element in the P collection. So this is kind of like unwrapping the list, okay. So and I just created this for simplicity, okay. So this is gonna be the P collection we're gonna be playing with in the rest of the exercise, okay. But again, this is another friend of Pardue, and if you want, so we can so you can actually try to implement it, okay. So well, let's actually do that as an exercise, okay. Let me show you how could I implement a flat map myself, okay. Let me actually do that, okay. So we have to create a class, my own flat map, and it has to extend from a do function, okay. And then, as we said, so we have to override the process method and do something here, okay. Well, so the input, each one of these inputs, okay, it's gonna be one line like this, okay. Okay, so we are gonna be receiving a line like this, okay. So this element, so we need to split it, okay. Let's say words are element, split it by space. So I'm gonna do one, let's say, flat map that is specific for this example, okay. we could try to do a flat map that actually receives as input and another a function, and then applies the function to each one of the elements, and then traverses the elements and so on. Just for simplicity, I'm not gonna do that here. Okay, and then for each one of the words, we just traverse it and we produce some output. Okay, so we just yield that word. Okay, let me see if this is correct. The code seems to be correct. And then here, instead of doing this, we could do something like this. Okay. A Pardue with my own flat map, and let's see actually if the output has the same aspect. Okay, so let's see if hopefully it will not fail. See, here is the same aspect here. Okay. Of course, if you're gonna be doing this operation, well, so I prefer to use flat map. So I recommend this in flat map. Okay, but this is just again to illustrate that there is no magic behind this flat map. Okay. So here we are just processing yielding one element for each one of the elements in a list, okay, in a collection, okay. And this flat map that we have done here, it's very simple, but we could have actually created a constructor, okay. Okay, so and accepting a function as input, and then using this function here. And then instead of doing this, okay, so we could actually try to apply this function to each one of the elements. Okay, let's see if this works like this. Okay, and then let's see if this doesn't fail. And then here we could use the same. Okay. Let's see if this works. Okay. See, again, the same result. Okay. So we have created just one flat map. Okay. Okay. And that behaves exactly like this one. Okay. So this, let's say, just helper code that makes your life easier, so you don't have to re-implement the same things over and over and over. Okay. So again, a do function is a very powerful thing, but Apache Beam already provides a lot of friends of Pardue with the higher level do functions that you can just use for your code, so you don't have to write them. Okay. Good. Okay. I hope this has been clear. Okay. So this is the constructor of the class. Okay. So the constructor has to have self as the first argument, and this is the argument that is passed here when we instantiate this class. Okay. So this is the argument that we have passed. It's a function. It's something that we may call. Okay. And here, when we have used the parentheses, we have actually called this element. Okay. So this is the beauty of Python, that makes it very simple to do this kind of things. Okay. And then the output here, well, we have set words because, well, so because we were splitting words, but let's say this would be the elements, the output elements. Okay. Okay. And then here we could, I don't know, like put like a little bit more of more meaningful names for the variables. Okay. So this is a flat map. Okay. And let me see if it runs, make sure that I haven't screwed up. Okay, perfect. Okay, it works. Okay, so this is a flat map. Okay, so this again is just another do function where, well, we haven't gone much farther than in the previous examples. Again, so we have only written the process method. We haven't touched any other method yet. Okay, so we will do that next. But here we have seen how to create a constructor for the class. So if we need to initialize it, okay, for some reason, like in this case, just to use a custom function that is applied to the element. So, well, we can perfectly do that. So we can put this as a member variable here, and then use that in the process method. Okay, I haven't mentioned that in the slides. So we have talked about the setup method, the teardown method, the start bundle, finish bundle, and so on, when each one of those is called and so on. But of course, the constructor of the class is another method that we may use to personalize our do function, okay? And the constructor is only called once when we create the instance, okay? Like here, okay? It will in reality be called once per worker, okay? Because we will have different instances of our code in different workers, okay? But this is another method that we can use to, let's say, to control our do function, okay? Just like any other class, okay? So this is the initialization of the class. And this works, let's say, exactly the same as in normal Python or Java or the language that you are using, okay? So you just, you may initialize any input argument that is passed to your do function by using the constructor, making it a member variable, and then using that member anywhere else in your class, like in the process method. Okay, good. Let me run this to make sure that we have the right copy collection, and this is good. Okay, so let's move on. Why am I using this example here? Okay, with this text and splitting this into words. Okay, so you have probably already found out that this is the typical example in any big data framework. Okay, so this is the example, kind of like the hello world of big data frameworks, is to count words in a collection of data. Okay, so this collection is really not big, it's just for the example, but it's a similar type of example. In order to count words, so we need to apply some cleaning. Okay, look at this. Okay, so this is in uppercase. Here we have a comma, okay? So if this appears more than once and we need to count it, okay? So we should rather normalize the text, making sure that we lower, for instance, all the instances, or we upper, and then before we actually count them. Or otherwise, if we have one lowercase here, it will be counted as a different word, okay? And saying here the word mancha, so it appears here with a comma, okay? Because it's with a comma in the original text. And if we don't remove this, if this same word appears with another symbol here or with no symbol, it will be counted as a different word. Okay, so we need to clean this. Okay, how are we gonna clean this? Well, with a do function, of course, or with a map. Maybe let's see that. Okay, so the cleaning function will receive as input a word, and it will produce as output another word that is clean. Okay, applying some process. Here I have already created this function for ourselves, okay, because it is not relevant for the sake of this exercise what transformation we are applying. Okay, just very quickly, we are removing the dots, okay, and replacing it by the empty character. Okay, we are replacing here the commas by the empty character, and then we are replacing here also the columns by an empty character, and then we are transforming to lowercase, and we are returning this. By all means, this is not an exhaustive cleaning of the word, okay? So we should do many more things in order to make sure that we are able to count words properly in a, let's say, in a real setting, okay? This is just an example for this exercise, okay? So let's actually start applying this to this collection, okay? So we are gonna take the words, okay, and we could just apply a map like we did before, okay? And here the input to the map has to be something that is callable, okay? So a function, a callable object, okay? Here we have a function, so we can actually, so we could do something like this if you want, okay? Lambda word, we are gonna apply the word like this, okay? But if you realize, okay, if the only input argument to this function is this, and it's the same input argument as to the lambda, okay, so we can actually just simplify this like this, okay, and use the name of the function as a reference, okay? And let me put this is clean, and let's have a look at this. Sanitize word is not recognized because I haven't run this down. Okay, now it should work. Okay, here it is. Let me just scroll up a little bit. See, this is now in lowercase, okay, as the transformation that we did, and mancha appears in lowercase and without the comma, okay? So now our words are ready to be counted. Here I have applied the map. Let me just, sorry. let me just let me try to make the same with a part do. Okay, so how do I do the same with a part do? Well, I have here to put a do function. Oh, okay, so let me create a do function. Okay. Okay, so I have do here the do function. I have to extend from do function. I have to override this process method. Okay, and the input is the element, and then I yield the result of calling sanitize word on this input element. Okay, let me see, and then here I can just apply sanitize word. Okay, I instantiate the do function. See, I'm not passing here a reference. Okay, here I have to instantiate the class. Okay, and this is the do function that is gonna be applied. Okay, so see, this is different than here. Here is a reference. Okay, because I may call this. Here I have to instantiate the do function. Okay, and then okay, see, same result. Okay, so this is the code. Okay, and similarly, as we did in the previous case, we could, so here this is a do function that only works with this specific function. Okay, what if I want to apply any other function? Well, so I could do that. Okay, I could just create here the constructor and pass a function. Okay, and then put it as a member variable. Okay, and then just call it here. Okay, and this that I have done is actually a map. Okay, so I have invented another map. Okay, this is my map, let's call it. Okay, my map do function. Okay, and then here I can just do my map do function sanitize word. Okay, and it should work in the same way. Okay, and again here I'm passing the reference. Okay, because this works exactly as a map. Okay, so I have invented the map here. Again, a map is only a helper function that is available in Apache Beam for your convenience. Okay, so you don't have to write all this code when you want just to apply a function. Okay, or create a do function that I created like the previous one that is actually specific just for one function. Okay, like wrapping a function around a do function. Okay, so that's really it's silly. Okay, so we shouldn't need to do that. Okay, moving on. So we have seen again similar example. Now we have this collection of clean words. Okay, and now we are gonna apply. Let's see here. We are gonna see, and let me fix also this here. We are gonna see how each one of these methods, tear down, setup, and so on, work. Okay. So here I'm gonna create this do function and I'm gonna apply it to our data. Okay. So for sure I will have to use here part do. Okay, because I cannot use this finish bundle, start bundle, setup method, all these methods. I cannot use this with map, with flat map, or with all these higher level functions. Okay, because those functions don't accept a do function as input. Okay, the only thing that accepts a do function as input is a part do. Okay, so if I'm gonna do fancy things using these methods, I have to create a do function and use part do. Okay, so let's do that. Okay, so I'm gonna make a simple do function for the moment. I'm gonna transform each one of the words into uppercase. And then I'm gonna put things in the different methods, okay, to actually have a look at how these methods work, okay. Okay, so let me put this here, and the process method is the first one I have to always override. Okay, this is mandatory to override. Okay, and I'm gonna yield element upper. Okay, for instance. Okay, let me see if this is correct. Okay, this is correct, and let's apply this. Okay. Let's put these transform words are the clean words, the ones that I have actually created before, and I'm gonna apply a part do, and I'm gonna apply my change word do function, and I'm gonna have a look at this P collection. Let's see if this works. Okay, so see, all the words are in uppercase, so this is working. I haven't done anything yet, okay, so this is the same as before. Now we're gonna start writing some methods. Okay, so let's actually create here the start bundle method. Start bundle method, okay. It doesn't receive any input, okay. So it's just a method that is called, okay. And we are gonna put here, and I have here, let me just put here some, and let me take some code, okay. So I'm gonna create a method here. I'm gonna be called like this, okay. Let's call now, okay. And it's gonna return this, okay. And I apologize for actually copy pasting code, okay. It's not my style, but I hate formatting dates, okay. And probably you do too. Okay, so this is just to provide some visibility on when each one of the methods is gonna be running, okay. So okay, so here, this moment, let's call this, and let's print bundle started at this string, okay. Let me run this, and let me run this again, okay. See, this method has been called. I didn't call it, okay. I just created the part do and the do function, okay. I didn't explicitly call this, okay. But this method, it was actually started at this moment, okay. This method has to be called after the constructor, okay. Let me put here a dummy constructor, okay. This moment is self now, and let's put constructor call at. We're not gonna see like a huge difference, or maybe no difference at all. So maybe I should use here milliseconds also, okay? Because well, so it's gonna be it's running, let's say, in local in my laptop, okay? So I did something wrong here. Let's see, not sure what I did wrong. Okay. Oh, of course, this is not S. This is this moment. Okay. Now again, okay. See, the constructor is called, and then after a while, the bundle is called. Okay. So well, after a while, after 3 seconds. Okay. Well, but we have seen the difference. Okay. So this was actually called here. Okay. When at this very moment when this was executed. Okay. But this method, the part do, is actually not executed until we call the run method of the pipeline, okay? And that happens when we do this, okay? This is actually just creating the graph that is gonna be executed, and at the moment of the creation of the graph, so we are actually calling this code here, okay? That's why this is appearing here, and then later on, when the pipeline is actually run, is when we see this, okay? And this has been a difference of 3 seconds in this case. Okay, what if I override the finish bundle method, okay? Well, let me actually, let me copy paste a little bit, okay? I'm gonna change this, and this is gonna be the finish bundle method. I'm overwriting this method, okay? And it's gonna be similar. Okay, so this is when the bundle is finished. And I think it's gonna be actually started and finished almost at the same second, because it's just 4 lines of text, okay? So it's really not a lot of processing, okay? And yes, so it actually finished in the same second, okay? Okay, so the bundle was started and then it was finished processing, okay? And this happens, okay, well, 4 seconds after the creation of the constructor, okay? We still have 2 other methods to have a look at, okay? So the other methods, okay? It's the setup method, okay? This method is called when the worker starts, okay? And I'm gonna put here the worker because here I'm actually using the interactive runner, so there are not many workers. It's just a process in my laptop, okay? But let's say the concept still applies, okay? If we're running in a distributed system, so this will be process that is actually running somewhere in a machine, etc. Okay, so let me see. The order, so I cannot save, I will make a copy later and I will share it later. The order in which I create these methods, it doesn't matter, of course, okay? So these are just methods that I'm overriding in, and it's the runner, the one that decides how and when these methods are gonna be called, okay? So this method is gonna be called the first, then this method is gonna be called the second, and this is gonna be called the third. And for sure, the order doesn't matter, the order in which I write the code doesn't matter, as long as, let's say, I'm just overwriting the right method, so that's what it matters, okay? Okay. Constructor call at 42. The worker started at 45. 1 second later, the bundle started, and then the bundle finished, okay? Again, see, okay, so this is the order, like setup, start bundle, finish bundling, which has been called, okay? And this is not the same order in which this is, okay? Just let me put here, I don't know, like for instance, here in the middle, let me put the other method that I need to call. It's called the tear down, okay? I have to put also the self, and with your permission, sorry, this is a colon, okay? With your permission, I'm gonna just put this, I'm gonna copy paste, okay? It's the same code, okay? So, and this is when the worker is finished, okay? Or is actually destroyed. Okay, so we have now the setup method and the teardown method. Let me put it in the right order. Okay, we have seen that the order doesn't matter, but let's say in chronological order. Okay, so this is well, for sure the first method that we're going to be calling is the constructor. This is called once when the worker is created. This is called once per bundle when it's started. Then this is the next one that is called when the bundle is finished. Okay, when the full bundle is processed. And then when the worker is not needed anymore, so we call teardown, okay? And then this is called once per input element. Let me see this here. Let's see, the constructor was called at this moment. The worker started, sorry, the worker, see, sorry. Worker finished, okay. Okay, and the worker is actually, it should appear twice. I don't know why it didn't appear, okay? Let me just see why it didn't appear when this didn't appear, the tear down. Okay, now, okay, so here it appears, okay? And if I put anything else here, just let's say just to show you that there's no trick here, okay? Anything else should, the syntax should appear there, okay? Hopefully. Okay, here it is, okay? So it was correct. Okay, so just let me remove it. It's working as expected, okay? Constructor, the worker was started, then the bundle was started at the same second. Well, it happened everything in the same second. Then the bundle is finished, and then the worker is finished, okay? And these two could happen more than once if we had a lot of data, that we don't for this example, okay? But if you run this, for instance, instead of taking the 4 sentences, well, I'm not gonna scroll up. So instead of taking the first 4 sentences of El Quixote, you take the full text, which is available in the Project Gutenberg as a public domain work. So you should actually see more than one bundle for sure, okay? Because well, it's really not huge, okay? But it's a couple of megabytes, 5 megabytes. So for sure you should see more than one bundle, okay? And then you can try with that example. Okay, so with this, we finish the example. Okay, so let me just make a copy. Okay, so I can actually share with you this code. Okay, just let me. But don't worry about this exact code because the solution is also here in the GitHub repository. Okay, so here you have this lifecycle with solutions. Okay, so this is the solutions of the exercises, and this is the blank one. Okay, but I'm gonna also upload this one with this very same code that I have actually used here in the session. Okay, so this was all, folks, and now I'm ready for your questions.
Thank you so much, Israel. Let me see. Sorry, I'm looking for the questions. Okay, so we have a couple at the Slack. This is a question for Alexander Sayenko. He says, I am currently using NextSpark code data frame for each partitioning. I think you should read this because this is a code that let me share it here. I'm going to share it here at the chat with you.
Yeah, sure. Okay,
so you don't have to jump to
yes,
another screen.
So question from Alexander so Pedro posted here. So and using NextSpark code. Okay, so this question looks difficult. Data frame for each partition group for each, but can't find any Apache Beam equivalent. How to get all elements collection from bundle? Okay.
And then if you see the reply, Alexander added the full version of the question.
I need to call external REST API endpoint to push records and extract some values from responses. But the problem is that this particular REST API works much more efficiently if I'm sending records group into 1000 records batches per each REST API call. So per element, per record basis is not a good solution. Totally agree with that. For this, because of poor performance, completely agree with that. I currently use the NextSpark code, data frame, partition, blah, blah, but can't find any Apache Beam equivalent group into batches. Not applicable. Totally, it's not applicable in this case because I don't have any key to group records into 1000 batches. Okay, this is actually a good question. This is a very good question. Okay, and I think I'm not gonna answer it here because this question is gonna be answered in the session of talking about the state and timers. Okay, so you need to group things into batches, and then for each one of the batch, when it reaches a certain size, like 1000 elements in this case, you make an external call. You're gonna see this example in the state and timer sessions, and I can actually share like a preview of this. Okay. Because this is actually so there's a post in the Beam blog, okay, and this batch remote procedure call. This is exactly what you're asking for, Alexander. So let me just put this in very quickly in the Slack. Not sure, I think you are there. Okay, so just pasting the link in the Slack. Okay, so.
And well, just to mention the state and timers patterns session. It's happening today at 8:30 p.m. UTC. So in case, Alexander, you want to join that session.
I strongly recommend it for you, Alexander, and for everyone, because this is this is the canonical problem that you solve with state and timers in Apache Beam. So this is what you're looking for in Apache Beam.
Great. The next question is from Amit Mondal. And he says, in which part of life cycle should we exception handling, say a connection dropped unexpectedly?
Okay, I think that probably should be in the process method. Okay, so let me go back to here in the code. Like when you are doing something here, okay, so you are doing the transformed element. So you are like, for instance, in this case, it's just apparent, okay. But say that you do something here with this connection or with these objects, and then this may fail, okay. So here you may try to do something, and if some except happens, okay. Well, so you can, I don't know, that you could create like a message, okay. Something fishy happens, okay. And now instead of yielding just one element, so here you may just yield the transformed element, okay. And if this, you can actually have, and this is kind of, I'm not sure when this is gonna be. This, okay. And let me just put this correctly. So this is the pattern, and this is what you are, let's say, looking for. This is what you're searching for, okay. So when something happens, when you're transforming the element, so you want to do something else, and typically, if you cannot recover from this error, so you want to produce like a dead letter queue, another parallel output with the some error message that will help you to debug what has happened. Okay. In the main document, the programming guide of Apache Beam here. Let me search for it. I cannot find it. Here, tags for multiple outputs. This is what I was searching for. Transforms, okay. Additional outputs. Okay, so this is, I think, let me just put again this in Slack. Okay, this is not exactly related to this session, but yes, I think this is what you need, Amit. So this is probably what you are looking for here. Okay, so having these additional outputs, and here, so well, in the web browser, I'm showing the Java example, but you can also see here the Python example. Okay, and this is very typically used to handle errors and to implement the letter Q in your transformations in your do function.
Our next question is from Steve, and he says, why does return work in this case instead of yield?
That's actually a good question that I don't know the full answer for. Okay, so return alone doesn't work. Okay, so it works if you return an iterable. Okay, so let me see here. Let me go back. No, or here. Yeah, let me go back. If I do this, this is not gonna work. Okay. Okay, so because this is not an iterable. Okay, but if I do this, because the output is iterable. Okay. The P collection will receive this element as, let's say, as element, okay, not the list, okay, the element that is inside the list, okay. I think that's why it works, okay, because this is iterable, okay. So, but return alone, this does not work, okay. So that's why I recommend you using here yield to implement like a generator and return always things that are iterable, okay. So, and same here with the yield, okay. So if I put this will not work, okay? So you have to put yield or like trick it into an iterable somehow, okay? But I don't recommend that, so just use yield.
And we have Íñigo San Jose, who is our next speaker, saying that this will be covered in the next session. I think This is related with your previous, comment.
Okay, great.
I think we don't have time for more questions, but we are adding all the questions to the Slack. So Israel can you can go ahead and take a look there, and I don't know, continue answering the questions at the Slack.
Sure. Yeah, I'll let's say I'll give a work in the channel in Slack, and I will try to answer some of the questions. Okay, so yeah.
Perfect. Thank you so much, Israel. Thank you, everyone. I know you have a lot of questions. Please be patient. Israel will be there in a minute, and we'll answer everything for you. The next session, I'm just hearing that the next session is at 1:30. Do you mind to keep answering right now, Israel?
Yeah, let's go. Let's keep answering questions. For sure.
So the next question is from Tudor. He says, how can I skip transformation from an element into a doFn? Say for an element that meets a certain criteria. I don't want to yield. How can I do that?
Just don't do it. So, okay, so I'm not sure if I can return to the sharing the screen. So I stopped sharing my screen. So maybe we can, let me share it again. 1 minute. I'm not sure if that's possible, like to have it in the video again. Okay, so like to show one, like a code snippet. Okay, now perfect. Okay, so say that in this transform method, I just want to, let's say, I want to only produce output if the element it fulfills some conditions. Okay, so I do this. Okay, I don't have to do here like, no, just don't do it, and you will have implemented the filter. Okay, so if you don't yield anything as output of your method, and let's say ignoring this. Okay, so just let me ignore this. Okay, so then that element will be just omitted and ignored in your code. Okay, so you just do it like this. Okay, so and this is the way you implement a filter, for instance. Okay, so this is the way you could implement a filter. So just don't yield it, and that's all right.
Perfect. So the next question is from Dan Young. And the question is there any way to adjust or configure the bundle size on, say, the read from pub stuff with subscription?
No. So the bundle size is decided by the runner. Okay, so it's a parameter that the runner decides, and it depends on different conditions. For sure, like Dataflow, Spark, Flink will use different values. Dataflow will use different values depending on the properties of the workers, depending on whether this is a batch or a streaming pipeline, and you cannot influence the bundle size. So no, so that's not something that you can change.
Perfect. And the next question is from Pierre. He says, where in the do-fm function do you keep state? And would you cover this in another session?
This will be covered in another session, and it's kept in the so-called state variables. Okay, but so more on that later in this another session.
Perfect. And the question from Pradeep, is bundle same as microbatch?
In a way, you could say so. Okay, so you are just splitting in micro batchings in order to process each bundle separately. So yeah, in a way, you could say it's micro batching. Okay, if the question is about the streaming and bundling and micro batching, then this doesn't affect the fact that you can actually group or elements, bundle elements together by event time, and therefore this wouldn't be micro batching in the sense of streaming, where you are just, let's say, splitting the data by processing time and not being able to reason about time for messages that fall in different buckets in this micro batching. Okay, then if the question is about that, it's not micro batching. It's not related. Okay, but yeah, if you can just say that, if you want to say that bundling is micro batching, yeah, for sure. So you have a big batch of data that are and you split it in small batches, so you can actually process it in parallel in smaller elements and in different workers.
Okay. And we have another question for Nikolai. And it says, is a bundle start or stop good place for logging? Do we have something here like execution context about P collection?
It could be a good place for logging. Okay, so probably a bad place for logging is the process method, because you are like you can be producing one line of log per element. That would be a lot of logging. Okay, and then that probably will have an impact in the performance of your pipeline. But bundling, like the start and finish bundle, will be called, let's say, one order of magnitude less times than the process methods. Okay, because elements will be grouping bundles in big bundles for some definition of big. So yeah, it's a good place to produce a log. Okay, and if you need some kind of context, okay, so well, so you have your member variables in your do function class, okay, that you may initialize or like set with some context when, for instance, when you're in the process method and you're receiving the process context, or at the initialization or at any other moment, and use those variables in the logging when you are using the start bundle. Okay, so I think it's a good idea to log at the start and the finish bundle, or at one of the two, rather than the process method, because you will be reducing the amount of logging. Okay, so yeah, for sure. And for the context, well, so it's a class. Okay, so just use members and other variables, let's say, to convey and values from one method to another.
Perfect. And we have another question from Andres. It says, I hear you say that it's better to use interactive runner to test your pipelines and monitor them. But in the last session, the presenter said that sometimes there are bugs with interactive runner. How can you monitor and test your pipelines from Dataflow?
Okay, not sure what those bugs are. Okay, so so we have seen that we have had quite a smooth experience here today with the interactive runner. Okay, but if you want to, let's say, test your pipelines, okay, not you don't have to do this with the interactive runner. Okay, so there's an object in Apache Beam that's called the test pipeline. Okay, so let me search for the link and I will post it here in Slack. And 1 minute because I'm going through the documentation, and this is somewhere in the website of Beam. I remember to see this somewhere. Okay. Yes. Well, I cannot find it right now, but I will paste it later. Okay. So yes, command line patterns here. I cannot find it right now, but there's an article about, here it is, testing your pipeline. Okay. Okay, so let me put this in Slack. Okay, where is the question? Here, Andres. Okay, let me put it as a comment in the thread. Okay, so this is the article I recommend you. So basically, you may just create an object for a test pipeline, and you have full control over the environment here. And then you may, let's say, emulate a runner with your test pipeline and test pipelines locally, okay, without having to run them first in a service. So if you are going to be developing a complex pipeline, I strongly recommend you implementing unitary testing, and the pipeline test also is in test pipelines. Okay, so Beam is prepared for this, and so this is, let's say, the proper way of testing things. Okay, the interactive runner is more for exploratory work that you are doing before you actually, let's say, write the real thing. Okay, so to be able to have some visibility about how your code is behaving. Okay, but if you are gonna be testing, like actual testing, so using test pipeline is much better. It's a much better option.
Perfect. We have another question from Pradeep. It says, how can I log all messages in a bundle or count bundle size?
Yes. Okay. Again, so this is probably gonna be covered in the state and timers option session. So you would have to keep a state variable that you would initialize in the start bundle method, and then every time you process an element, you increase that variable. Okay. And then in the finish bundle method, for instance, you just put it in the log. Okay. And then that variable will contain the number of messages that were in that bundle that was just processed. Okay. But for that, you need to use a state. Okay, and so I recommend you to attend the state and timers session, because that's probably, I'm not sure if this specific example will be covered there, but with the contents that you will see in the session, so it will be probably easy to implement afterwards by reusing what is shown in the session.
Perfect. Well, we don't have any more questions right now. And thank you a lot, Israel, for having all these resources and be so quickly jumping from one application to another and sharing everything. And well, just want to let you know, Israel is going to be providing other courses during the program. And please also take a look at the program so you can tell which specific, sessions you need to attend, or, anything special. And Israel is going to be at the Slack also, as well as the other speakers. So please feel free to keep asking there. Tag him if you have a specific question for him. If not, we will try to monitor the Slack as also the YouTube, and add the questions to the Slack and tag the speakers. And well, we are going to be back in 15 minutes, I guess. Yes, 15 minutes with our next session. Well, thanks a lot, Israel, for the session, and thanks a lot to all the participants. See you in 15 minutes.
Yeah, thank you. Thanks.
Thank you.
Bye.
Hello, everybody. Welcome to our next session at Beam College, where we will talk about branching and merging P collections. We have Miren Esnaola and Inigo San Jose, who will be leading this session. And this session will be divided in two parts. First, we will focus on branching P collections. We will do, Miren will do a presentation, then we will have a walkthrough, and then we will address questions on branching P collections. And then we will go to the second part of the session, which will be focused on merging those P collections. So again, we will do a bit of theory, review the slides, and then we will do a walkthrough. And remember that all the resources are available in the GitHub repo. We will post it in the YouTube chat in a couple of seconds in case you don't have it. Having said that, Miren and Inigo, please go ahead. It's a pleasure.
Hi, thank you, Pedro. So yes, as Pedro was saying, in this session we are going to discuss two very common patterns that you will certainly need to use when designing your Apache Beam pipelines: branching and merging P collections. We will see that each of the patterns can be implemented in a variety of ways depending on our use case. So let's get started with the options that we have when branching P collections first. So the first option we have is the one that you see on the screen. You can use the same P collection as input for multiple transforms without consuming the input or altering it. In the example, for instance, we are reading a collection of names from a database, and we are using two Pardue transforms to filter the same P collection, and keeping the names starting with A in one case and the names starting with B in the other. There's another way to branch a pipeline, and that is to use to have a single transform output to multiple P collections by using tagged outputs. The transforms that produce more than one output process each element of the input once and write to 0 or more output P collections. If we try to compare this pipeline and the previous one, you can see that they perform the same operation in different ways. The second approach performs better if the transforms computation per element is very time consuming. Okay, so choose that one in that case. And then there is a final way to branch P collections that is to use the partition transform. That is another one of the Apache Beam core transforms. This transform, what it does, it splits an input P collection into multiple smaller output P collection, and it does it according to a partitioning function. The number of partitions must be determined when the graph is constructed, okay? So you can, for example, pass the number of partitions as a command line option at runtime, and then it will be used to build your pipeline graph. Or you can, but the thing is that you cannot really determine the number of partitions in the middle of the pipeline based on some data calculation that you might be doing in the pipeline, okay? So let's see in a diagram how the partition transform works, okay? So you see there that we have an input collection. The elements are colored shapes, and we want to split it in 3 P collections, each of them containing the shapes of a specific type, okay? So the partitioning function, what it's going to do is going to check the shape type, and it's going to return a number identifying the output P collection that the element belongs to. So 0 for squares, 1 for circles, or 2 for triangles, okay? If we move to a more practical example, we have read a P collection of names from a database, and we want to split them alphabetically. that's really a perfect use case to use the partition transform. Using a partitioning function that takes the first character of the name, and based on its value, it returns the partition number that the element belongs to. So for instance, 0 for A, 1 for B, etc. So let's now, we have Inigo here, and he's going to run a few examples demonstrating all this in a code lab, okay? So
exactly. Thanks a lot, Miren. Let's now head to Google Colab. You also see the link to the Colab in the chat, in case that you want to follow along with me. I will try to go slower than yesterday, but I don't promise anything. I will do my best, that's for sure. So the first thing you need to do is to install Apache Beam running this cell. I have already done it, so you don't have to wait. And next, you're going to import everything that you're going to need for the session. So in case that you run into any error running this particular cell, you will need to restart the runtime. So you can go to runtime here. Let me make it bigger. You can go to runtime and restart runtime. So with that out of the way, let's start with the actual code. The first example we have here is the first example that Miriam explained. We can use the same P collection as an input to perform different P transform. In this case, we have this set of elements that are dictionaries. Imagine that those are a table. We have a column called names, another column named sports. And we're going to create those using the create transform. The create transform is a very easy way to create P collection without needing to use file system or accessing a database. And it's very practical for these examples. So we are assigning to this P collection that we're creating the variable, the P collection variable elements pcall. And just by referencing those two, we can perform different P transforms. In this case, we have names that what it's going to do is perform a map function with a lambda, and it's going to retrieve the name column. And we have the same for sports, that is going to retrieve the sports column. Let's run the cell. The same as Israel, I'm using Interactive Runner because we get this beautiful graph that you see here, and it's very useful for this scenario. So we have the create, our P collection variable, and now we have this branching of the pipeline. We can see that we get two results. The first one, names, with the names column, and the name, the sports P collection with the sports column. Okay, that was easy. Let's continue with partition. That was another example that Miren showed. We need partition, and because sometimes we want a specific element to go to a place and not go to the other. And with the previous example, this possibility is not covered. So partition, what it does, it takes an element, applies a function to it, and depending the output of this function, it will send it to one place or the other. The output of this function should be the index to which the element should go to. I have an example here using partition. The idea is that we are going to split elements by even or odd, and we are going to create the elements using range. So we're creating elements from 0 to 9, and now we're going to perform the partition. I'm using a lambda function that has two variables, and a partition. The first variable here is going to be the elements, what we're going to do to the elements. A partition should be the number of partitions that we have. In this case, since we're going to be split by even and odd, we're using the modulo function, and depending on the index, we will send it to one or the other. So for example, if we take number 5 modulo 2 is 1, and it will go to the index 1, which is odd. If we take number 8 modulo 2 is 0, so it will go to index 0, even. And in this side, we just have the number of partitions that we needed. In this case, since it was even and odd, we have 2, so let's put a 2 over there. Let's run the cell and confirm that this works. And here we go. We get the even numbers and the odd numbers. Just so you get the hang of it, let's modify this to retrieve, instead of even and odds, we're going to retrieve multiples of 3 plus 1, and multiples of 3 plus 2. So I'm going to change this to zeros, ones, and twos. we're going to create the same elements. This lambda remains the same, but we need to change the modulo to 3 because we are calculating things modulo 3. And since we have 3 partitions, we do a 3 instead of a 2. Let's now take our picolation variables here that we're going to print using id.show. And this is running, and we get the multiples of 3, multiples of 3 plus 1, and multiples of 3 plus 2. Okay, let's see a very common use case for partition. Let's say that we have a data set, and we want to split our data set in test and train just to perform some machine learning operations to it. In this case, what I'm doing is creating 100 elements, and I'm going to just split them using partition. So I have set a percentage that I want to split the test and train data for. And the function that we are applying to the elements is just generating a random number and comparing it to the percentage. In case that this is lower, this will be true. And when we calculate the integer of a Boolean being true, it returns 1. So it will go to train. In case that the random generator returns a 0.99, this will be bigger than percentage. So the Boolean will be false and the integer will be 0. It will go to train. Let's run the cell and we see how well our split is. So we got 92 elements for train and 8 elements for test. Of course, the split is not perfect because we're using a random generator. If we increase this to 10,000, this will be better. Let's wait for it. It will take maybe a little bit more. And we get, well, not such a good split, but well, mathematics, right? Sometimes it works and sometimes it doesn't. Actually, it always works, but okay. So this partition function doesn't cover all the possibilities yet. What happens if we want to one particular element to go to more than one place? This is what Israel was showing you in the previous session. With the error handling, you can tag the outputs with a Pardue. So this code here is a little bit hard to understand. I will do my best, but in case that my explanation is not the best and you want to try it later, I have everything written here. So let's go through the code together once. I'm creating 8 numbers, and the idea, and then I'm doing a Pardue. The idea of the Pardue that we have the class here is that we're going to output to 3 branches. We have multiples of X, multiples of Y, and the main output. Notice that in the process, we have three parameters. We have self, of course, and we have element, which is the element that we are sending to the Pardue, but it's coming from the previous transform. We have X and Y. And the way we are specifying this X and Y is just adding quarks to our Pardue. So we're doing X equal 2 and Y equal 3. So we're checking multiples of 2 and multiples of 3. In order to check that, we do again the modulo function, checking if it's a multiple of X. And in case that this is true, we yield this to a tag output. We use pvalue.tag output and we send the element here. How do we send it? So the first part of the parentheses has to be the name of the tag. In this case, I'm naming it X. And the second part is the actual element that we are outputting. In this case, I'm just outputting element, but in case that I wanted to output half the element, I could do it like this. And now the element that we're actually outputting is half the original element that was introduced to this part. But let's leave it like that. We want to get the actual multiples. We do the same to Y. If it's a multiple of Y, we output to this particular tag named Y. And it doesn't matter what, we have a main output with all the elements. Now that we have our Pardue, we need to tell the ptransform Pardue which outputs we're using. So we have X and Y, which we will say without outputs, and the name of the tags that we're using. So if we run this, we will get a pcollection tuple variable called diff_outputs. And in case that we want to retrieve the pcollection for our particular branch, we can do it in different ways. One of the ways is just using the pcollection tuple variable and doing dot the name of the tag, which is going to be X and Y. And we can also do it as if it was a dictionary and do X. For Y, we do exactly the same. And for the main output, we do just none. So diff outputs, brackets, none. Let's run the cell, and let's hope I didn't make any mistake here. We get the 3 branches, the multiples of x. Let's go back here. Multiples of x, multiples of y, and all the outputs. So we get multiples of x, which are the even numbers, the multiples of 3, and all the outputs. Notice that 6, that is a multiple of 2, multiple of 3, it's also in the main output. So we get an element that went to more than one place. And the same with 0, for example, it went to all the branches. Again, if this explanation wasn't so clear to you, I hope it was. You have the code here, the explanation here, so you can go through it later and check it out. This was my part for the splitting of the P collections. Let's see if you have some questions that I can address or Miren can address.
Yeah, we have a question in the Slack.
Is there a... Sorry, Miren, go ahead.
No, you, please.
Is there any way to dynamically create tag outputs while the job is running? Or do you need to know ahead the time when the job is submitted to Dataflow? As far as I know, I'm 90% sure, give me a 10% margin, you need to know it beforehand. I think it's exactly the same as partition. You need to know how the graph is going to be determined beforehand. But if you need to determine the things on runtime, maybe what you can do is, instead of outputting the element itself, create a key and then use another pardo or another combine or something. Combine will be addressed on the next session. Maybe you can perform an operation depending on the key that you have there, and you can define the keys dynamically. But I'm going to go to up to 99% sure that you cannot split things dynamically.
Okay.
Miriam, maybe you know better than me in this.
I think you are right that you cannot really work it out at runtime yet. So I mean, he seems pleased with your answer. So
okay, that's good.
So any more questions, guys, before we move to the merging P collections part?
Okay, so I guess it's back to you, Miren.
Yeah, okay, cool. So yeah, let's look now into the merging P collection use cases. So one of the ways that we can do that is to use another of the core transforms of Apache Beam. That's the flatten transform. What does flatten do? It just merges multiple input P collections with elements of the same data type in a single P collection, okay? So looking at it in this diagram, we have 3 P collections of shapes, and the flatten transform simply merges the elements in the P collections to create another P collection containing all of them as output, okay? So going to a more practical example, okay? So this example, it's actually a continuation of the first example that we saw at the beginning of the session today, when we had done some branching of an input P collection into 2 P collections, one with the names starting with A and another one with the names starting with B. So what we could do here is introduce a flattened transform. So we created a P collection that included both the strings with A and the strings with starting with B, okay? Very simple. What's the next way of merging 2 P collections? Another core transform of Apache Beam, the cogroup by key transform, okay? So what does this transform do? This transform performs a relational join between 2 P collections, okay? The collections must be keyed, so the elements have to be key value pairs, and the key of the collections that are in the input have to be of the same type, okay? So going to the diagram, we see it quite clearly there, right? So we have 2 P collections that are keyed. Like, I mean, the elements are color shapes, and the key of the element is going to be the color of the shape. So green, orange, yellow, and the value is going to be the type of shape, okay? A square, circle, triangle. So we do the co-group by key transform, and what we are going to do is like to join both P collections by the color of the elements, okay, into a single one. And the key of the elements is going to be in the output, it's going to be also the color, and the value of the elements is going to be a list of the shapes that have that particular color, okay? So, like with a more tangible example, we have in the figure the pipeline that is reading. For instance, imagine that we have a shop and it's reading the names and the addresses from a database table. Okay. And the names and the orders or the order numbers of the purchases that customers are doing are coming from a Kafka topic. So the pipeline, it's going to use a co-group by key transform to join both collections, okay? Because the key is the same, the key is the name, okay? And the resulting P collection is going to have is going to be keyed by name, and it's going to contain, like per key, the order, the orders and the addresses, okay, belonging to that customer. And then the final scenario that we have for you is to use side inputs, okay, to merge to do the merge. What is a side input? A side input is some kind of additional input that a do function can access each time it's going to process an element, okay? And the element that we have in the collection, that collection is called the main input, okay? So we have the side input on one side and the main input. When you specify a side input, what you actually are doing is to create a view of some other data determined at runtime, okay? So such values might be determined by the pipeline input data, or they can depend on a different branch of your pipeline that resulted in a P collection, okay? So you can take that P collection in that other branch and create a view, and that is the actual side input. You are going to see this very clearly in the following example, okay? So we have this scenario here. We have a website that is, imagine, selling construction materials for builders, things like concrete, bricks, etc. And whenever a builder makes a purchase, an event is published in a Kafka topic, okay? So our customer base, I mean, let's imagine that it's quite small, that we have less than 1,000 builders that are using our services, okay? So therefore, we can perfectly read our customer profiles from the database table into a P collection and keep them in memory, okay? That is going to be our side input, okay? And in case that we need to generate, for instance, the invoices for the purchases that our customers are making, we can pass the side input with the customer profiles to a Pardue transform, and for every incoming purchase, the transform is going to be reading the address from the corresponding customer profile and generate the invoice and write it to the output P collection, okay? So this use case that we are seeing, the side input had like a global window. We did not have any windowing in the side input. What would have happened if our side input would have been also windowed, okay? So we said that a side input is some kind of view of some data, okay? And when the data is windowed, the view, like when we have a windowed P collection, the view represents a single entity per window. It can be a value, it can be a list, it can be a dictionary, okay? And how does Beam act in that kind of a scenario? Beam projects the main input elements window into the side inputs window set and uses the side input of the resulting window, okay? So if the windows are identical, the projection returns exactly the same window for the side input. But, however, if they are different, the projection is used to choose the most suitable side input window, okay? Couple more things that you have to take into account. What will happen when the main input element exists in more than one window? As when we use, for instance, sliding time windows. In that case, the element is processed once for each window. Each call is going to project the current window for the main input element, and the result, it can result that we can have a different view of the side input each time, okay? And then finally, what will happen if the side input has multiple trigger firings? In that case, the value from the latest trigger firing is the one that is going to be used. We can see this in a practical example. So let's go back to our shop example and consider what will happen during the sales season. During the sales season, we will have discounted prices, and the discounts will be larger as weeks go by, okay? So if we want to generate, for instance, a report on the daily sales that we have on the shop, our main input would still be the purchases peak collection that we saw before. But in this case, we would be using, for instance, a fixed one-day window to calculate the total money that we are making every day. And the side input is going to be a peak collection with the discount rates, okay? But they are going to be window by week because the discount rate is changing every week, okay? So in order to calculate, to make their daily report, the discount rate corresponding to a particular date, the report is generated, is going to be obtained by projecting the purchases window over the discounts window, okay? And we are going to get back a single value. That is going to be the discount rate for the week that the purchase belongs to. Okay, so that's the way to proceed when the side inputs are windowed. So now we have a few more examples from Inigo, where he's going to apply all these patterns. Okay.
Yeah, thanks so much, Miren. So let's get back to our Colab, and the first example we're going to have here is flatten. The easiest of the ones we're going to have. So we're creating two P collections. We have elements 1 and elements 2 over here, 3 dictionaries in each, the same table as we had before with names and sports. And we're creating these two P collection variables. We're creating create 1 and create 2, a very original name as I'm font 2. So now we're going to flatten those. More or less, the idea of flatten is like a union in SQL. So you're putting them together, like adding them up. So what we need to do flatten is on the left side of the pipe. This is what I'm calling pipe, by the way. We need to have a tuple with all the P collection variables that we're going to flatten. And on the right side, we just need the flatten. So let's run the cell and see how this goes. We again have the beautiful graph coming from Interactive Runner, and we get all the 6 elements as a single P collection. We can see that the same 3 we have here and the other 3 we have here, they are being put together into one P collection. Okay, it was very simple. Let's go to cogroup by key. The idea of cogroup by key is very similar to a group by key, but instead of doing a group by key with one P collection, we can do it with multiple P collections. And we will get the combined element of all the group by keys. The way I think of a group by key is something very similar to a group by key plus a flatten. That's the way I think of a group by key. So let's see the example, and I think you're going to get this more clear. So I'm creating 2 different data sets. One is going to be jobs, and the other one is going to be hobbies. The elements in jobs are key values, where the key is going to be a name, John, Rebecca, Alice, Charles, and Ruben, and the value of the key value is going to be the job. And the same way with hobbies, we have names as keys, and the hobbies they have as values. Now I'm going to create these two P collections using create once again. Very easy and fast. And now I'm going to group by key those two P collections. The way I do this, on the right side of the pipe, just group by key. And on the left side of the pipe, I can have either a tuple, as we had on Flatten, or we can actually have a dictionary. The keys of the dictionary is something that we define, that we can say whatever here. And the value of every key has to be one P collection variable. So for jobs, I have the P collection jobs creates, and for hobbies, we have the hobbies create. Now, these keys here will appear on the output of the group by key. Let's run the cell and let's see what the output is and how it looks like. We again have the graph, the two branches being merged together into one. So the output is a key value, where the key is the same key that we had on the previous P collection, the names in this case, so John, Rebecca, Alice, Charles, and Ruben. And the value is going to be a dictionary with the keys that we defined on the group by key, jobs, and hobbies. And the value of those keys is going to be the group by key result that we will apply to that P collection. So we will get the group by key of jobs create and the group by key of hobbies. Let's check the data we have here. John, for example, was a data scientist and a data engineer and had hobbies, baseball, and piano. If we go back, we see a list containing data scientist and data engineer, hobbies, baseball, and piano. If we check Rebecca was a full stack engineer and hobbies, football, acting, and reading. And if we go to Rebecca, we can see those values. Notice one thing here. Ruben had a job, tech writer, but Ruben didn't have any hobby. And I'm sorry, Ruben. I thought it was better for you to have a job and miss a hobby than the other way around. And if we check the output, we can see that Ruben had a job, but the hobbies was an empty list. Now, this group by key is very useful when we want to do a join, like we will do in SQL, and we can actually take the same output we got from the group by key, and with some transformation, we can make it the typical join in SQL. So this is the function that we have here. I'm referencing group by key, which was the output we got on here. This is the P collection variable, exactly this one here. And we are going to do a flat map to it. So since we need to output more than one element per element, we need a flat map or a per loop. So this is the function we have. Name is going to be the key. So we're doing element 0. So it's going to be the name, Alice, Charles, whatever. And the jobs is going to be the value, so element 1, and we check hobbies. We check jobs, so we will get the data from here. And for hobbies, we do the same. We check the key hobbies. And now with double for jobs and for hobbies, we will get all the possible combinations. And since join is a list, I can use it directly and I will output everything there. So let's run this and we will get all the combined elements as an inner join. So we get join, that was data scientist and baseball, John, that was data scientist and piano, the other hobby, data engineer, the other job, and baseball and piano. And notice one thing, Ruben doesn't appear here. This is because we are doing an inner join. So when it goes to here, Ruben wouldn't appear. Again, sorry, Ruben, it's nothing personal. So now I want to explain the last method that we have on this session, which is side inputs. The idea of side inputs is that P collection can also take, pipelines can also take P collection as parameters using these side inputs. They can be viewed as dictionaries, as lists, as a singleton, and some other ways that you have here in this documentation link. We normally use side inputs instead of group by keys when either our data that we're using in the side input doesn't relate key by key to our main input, or maybe we want to enrich our data. There's another idea that side input is helpful for. This is when we want to join our data as we will do with group by key, but we have a rather big left data set and a rather small data set on the right. This is something that it's called broadcast join, and I will go through it a bit later, so you can see and get the hang of it. So first, let's go to a simpler scenario. This is the pipeline that we're going to run here. So I'm creating some values that have a currency column and an amount on there. As you can see, these numbers are very famous if you like mathematics, and as I do. And then I'm going to create some rates. These rates are going to be our side input. I'm going to use this example of changing currency in pretty much all the examples for side inputs. So just FYI, so you know this beforehand. So the first thing I'm doing, I'm creating my side inputs using a create, and I'm going to create also my values using another create here. So we have rates and we have our main pipeline, which is going to be exchange. Now I'm going to do a pardo. I'm going to call this function here, change currency. And notice again that we have two parameters for this function. We have value and we have ratios. And instead of sending a fixed value as we were doing with the splitting, what I'm doing is sending a p collection. The way I'm doing that is just doing p value as dict. So I'm viewing my data as a dictionary and the p collection variable that we had over here. And if we go through change currency, this is nothing super interesting for Beam, but in case that you want to check it, it just goes through the ratios and multiplies the value depending on the key. Nothing too important for the session. One important thing that I want to say is that when we're doing ASTIC, the input p collection has to be key values. You can see that here we have euros and the value of a dictionary here, and the same for the other ones. And let's run this thing here. Actually, let me print the ratios here so you get how the p collection looks like once it's converted to dictionary. Notice that this is going to be executed for every single element since we're doing a flat map. So since we had 3 elements in our value, we're going to print 3 times our ratio, because ratio is going to be called for every single element, as Miren said before. So this is how our side input looks like. We have a dictionary here with the keys and the values for every currency. And then we get the actual value once we have merged everything. Let's now go to the join that is very similar to the group by key, and actually going to use the same example as before, the jobs and hobbies example. And I want to explain once again why this is helpful. When we do a group by key, what we're actually doing is we're shuffling all the elements, and we're sending all the elements key by key to different workers. And this is something expensive. Shuffling is a very expensive operation. And sometimes we just don't want to do it because it will take more time than not shuffling. But if you want to join, you have to do it. The other approach is using these side inputs. When we do a side input, we actually need to materialize our side input since it's going to be read by all the workers. But we don't need to shuffle our main data. And every element that will execute will reach this side input, but we don't need to shuffle it. So if our left data set is big, we will avoid shuffling the big data set, and we just only need to shuffle and materialize our small data set, which would be right. In this example, I'm going to imagine that jobs is rather big and hobbies is rather small. So we have, again, hobbies. I'm creating them, and I'm going to group by key those p collection. I will explain why later. Then I'm creating the jobs, cyclic with a create, and doing a broadcast joint. By the way, I forgot to say that this approach of using side inputs, it's called broadcast joint in some other frameworks, like for example Spark. So we reference the main output, which is jobs create, and we do a flat map. Flat map is going to be calling this function over here. And again, we have the elements and the side inputs. We send our side input as a dictionary after grouping by key. The idea of grouping by key is because we want to retrieve all the elements that had the same key here. So we will get John with baseball and piano instead of getting just one of those. So let me once again print the side input so you get it, how it looks like. We get the graph once again. And if I didn't make any mistake, this is how our side input looks like. We get the key and the result of the group by key. So we get all the elements as a list, and we get the actual value. Check again that Ruben, as in the previous example, does not appear because we're doing an inner join. I'm going to show you this example once again, but instead of doing as a dig, I'm going to do it as a list. So let me move this. And now I don't need to group by key, so I'm removing this. I'm going to change. I need to change this. The idea is that here I was accessing to the side input by key since it was a dictionary. Now we don't need to do that, but I'm going to go through the code once with you. So we're retrieving the key of the element, which was the name. So element 0. Then we're getting the value, which was the job. So element 1. And now to access the side input, we just use side input here. And since it was a dictionary, we do get and the name, which was the key that we had before. Now this wouldn't work, so we need to change it. Let's do hobbies equal x0, which is x1, which is the hobby for x in side input. And this will go through our list and output the values, but we don't want all the values. We just want the values that share the same name as our element. So if x0, the key of the side inputs, is equal to name. And if we do this, if I didn't make any mistake, it should be exactly the same, but as a list. Notice that now this is not a dictionary, it's a list, because we were using as a list instead of as a dictionary. Of course, this will be worse performance because we will need to check all the elements in every single, all the side inputs in all the elements instead of just checking the key. Okay, to finish off, we have the side inputs and windows, and I have a picture here of how this works, pretty much the same as Miren had. So when we have side inputs and windows, we need to project upwards from the main to the side inputs. In this case, we have fixed windows for the main output and of 50 seconds, and the side input is going to have 100. So in this case, A will go to 1, B will go to 1 again. Now we're changing the window to 2, and then C will go to 2, and D will go to 2. We have this as an example. Again, I'm using the change currency example. I'm sorry, I'm not that original. So I'm creating some values. In this case, the table is going to have an amount and a timestamp column. This timestamp column is going to be used to add metadata to our element, so Beam knows when this element was generated. I think Reza in the first session was using a similar approach to with the test stream examples. And we do the same with rates. We have rates 91 for timestamp 0 and 88 for timestamp 100. We are creating the elements, adding the timestamp window, and in the case of the side inputs, we just care about the rate. We're dropping the timestamp, so we just do x rate, and we're adding a window of 100 seconds. For the change, we do exactly the same. We create the values at the timestamp, but in this case, we output absolutely everything. So we will get the whole dictionary, adding a window of 50 seconds, the same as we had here. And now we are doing a part2 to change the currency. So instead of using dictionary or list, I'm doing a singleton because I know that per window I have one element. So from 0 to 100, I have 91, and from 100 to 200, I have 88. Let's run the cell and let's see the output. So for 10 timestamp 0, so it was the first window for both, we get 91 as a rate and the converted value. For 5, it was the second window for the main output, but the same window for the main for the side. So the first value, which was 91, and the converted value. Now we change once again both the side and the main input, the main variable, the main window, sorry. And now we get the 88 because this was timestamp 100. And if we go back here, we will see that this is 100. Let's play a little bit with this. I'm going to change the window of the main input to 50. Let's run this thing and let's see what happens. Spoiler alert, is going to fail. But let's think about why. It's telling me that we have empty side input. So let's check our data. We are creating elements of Windows with windows of 50 seconds. But if we check our rates, we don't have any element between 50 and 100. So when the Beam tries to retrieve the element for that window, it's going to say like, hey, I cannot join it with anything, but what do you want me to do? So I'm going to fail. And it fails. How can we fix this? We have two ways. One of them will be, of course, adding one element here. So doing this and changing, I want to change this. This will make it work because now from 50 to 100, there will be values. But there's another way when we're using singletons. We can say like, okay, in case that there's nothing, use this default value. Default value. I'm going to do 1. So in case that window specifically doesn't have any element, just use 1. Let's run the cell. And here we go. From 0 to 50, we got 91. From 50 to 100, which was failing before, we get the default value of 1. And just to finish off, I'm going to show you a streaming example. Please notice that this requires Dataflow access and GCP access because you will need to create a subscription to it. And if you run this cell right here, it's going to fail because, first of all, Dataflow runner is not imported, and you will need the options to access your own project. So I have already prepared this pipeline. I have it running on my project. So let's go to it. And this is the pipeline. So actually, let me go back and explain the code because I didn't do it. So we're creating, again, our rates, key values, and we're going to make them dictionaries, pretty much the same as we did before. And we're going to read from this topic. This topic is the same topic I used yesterday. For those who weren't there, this is a public topic that publishes messages automatically. You don't need to do it yourself. And it contains many columns. The ones that are important for this is, so these are taxi drives that are happening, I think, in New York. And they have a column called ride status. And they can be either en route when the taxi is driving, pick up when it's picking up someone, and drop off when it's dropping off someone. So we only care about that one. So we're filtering using drop off. And now we're going to create a dictionary out of that, with the ride ID, something unique for the ride, and the meter reading. This is the amount of money that you need to pay when you're dropping off. To the change currency in this case, it's going to just convert this meter reading from dollars to euros and to Swiss francs. Yeah, let's go through it, and we can see that we're reading from PubSub, doing so and so. And if we go here, we can see that the log, we have the ride ID. I think this is too small. Maybe like this is better. I think it is. So we get the ride ID, the meter reading in dollars, 12.8, the meter reading in euros, and the meter reading in francs. Notice that here, I didn't need to add any window. This is because both elements, both the side inputs and the main inputs, fall within the global window. And I think this has been everything. I hope I wasn't so fast like yesterday, and you at least got 90-something% of this. Let's see if you have some questions, and maybe Miriam and I can answer them. Is there any question there?
So there was a question about CDC streams. I already answered it. Like there was a talk last year about processing CDC streams with Apache Beam. So in the Beam Summit.
Yes, so far that was the only question by Kathleen Kong. We're waiting to see if we receive any other questions from the YouTube stream.
I never know if not having question is good or bad.
Yeah, and when we do on-site events, usually you say, okay, if there's no questions, then there's claps. But here, I guess on online events, it's like, well, if there's no questions, then there's thumbs up, there's like.
Yeah, I also think Ruben is very upset. Yeah. Maybe next time I do this, I will change the name, and Ruben will have like 2,000 hobbies.
I think there are some questions coming. I see people writing.
Okay, let me check the YouTube stream.
Claps. Okay.
Can I explain again? Can I explain again the difference between inner join and group by key? Yeah, so group by key, well, inner join, I assume that you're saying group by key. Let me actually, maybe I have time to do an example directly here. This is the group by key.
Whoa. Sorry about that. There we go.
Okay, so this was the result of the group by key. I'm assuming that you're meaning inner join. With inner join, I think you're meaning group by key. Let me know if I understand them wrong. So let's check, for example, John. That was that we get a dictionary with jobs and hobbies and these two values. These two values are individually grouped by keys. Let me try to run something fast. Maybe I'm going to do it here. So I'm going to create a pipeline. Whoop, this is going to fail. I'm going to create this and doing a group by key, and IB show just create. Let's call it group by key. IB show group by key. So now I'm grouping by only the jobs. Instead of doing both with a group by key, I'm doing it just with one. And I fail somehow. Group by key is not defined. Okay, so.
Bin.
Yeah, exactly. So now we have only the elements by themselves. So we get the key and a list. Actually, it's an iterable of all the elements that share the same key. So for John, we get data scientist and data engineer. For Rebecca, full stack engineer. And in this case, since they only had one job, let's add something to Ruben. So I think it's spelled like this. So now Ruben is a millionaire. So we can get this new value for Ruben. So it's pretty much like joining everything together and putting the things with the same the things with the same key as a list. In this case of the group by key, we're doing exactly the same, but the result is going to be just adding things together, like just one single element. So jobs will have the group by key result for jobs, and hobbies will have the group by key result of baseball. Was this helpful, Andres? Thank you, Adelina.
Okay, we're about to be on time. So I guess we're gonna leave it there so that we leave 5 minutes before our next session. Thank you so much, Miren.
Yeah, we will be around in Slack for a few minutes in case some people have some more questions.
Sure. Thank you, Inigo and Miren. And the next session is advanced grouping and aggregations. And that should start in 6 minutes. And actually, Inigo, you're leading that one, right?
Yes, I am. Yes, I am.
Okay, so we
5
will
minutes
see.
break will work.
Okay. Bye, everybody.
See you in a second.
Hi, hello again. We are in our next session, and here is, you know him, Íñigo San Jose from previous session, and you will be looking at him and other sessions here. But right now, he's gonna share with us about how advanced grouping and aggregation and use notebooks for examples for combined by multiple keys. And well, I'll let Íñigo to start his session. This is a 30-minute session, and we have
Yeah, more or
time
less.
for questions and answers. So, well, go ahead. Welcome, Íñigo.
Thanks so much, Mara. So yeah, I'm Íñigo San Jose, Technical Source Engineer at Google, in case that you were not in the previous sessions that I imparted. And now I'm going to talk about how we can aggregate P collections and how we can group them using Apache Beam. So let me move the slide. This is the agenda that we have for today. I'm going to start explaining what's a combiner. Then I'm going to show you some built-in combiners and how we can customize and create our own combiners. Last, I'm going to show you something that we call combiner interface, that it's used to create more advanced combiners. And at the end, I'm going to show you everything with a demo as we did before using Colab. So first, what's a combiner, the definition and the types. Combiners are P transforms that aggregate our P collection. This is that we are going to output from multiple elements from our P collection. We're going to output one element or one element per key. We have two types of combiners. We have global combiners that aggregate our input P collection into one element or one element per window if we're using Windows, and per key combiners that, as the name says, aggregate our P collection of key values into one output per key, and of course per window in case that we're using Windows. This is an example with a visual cue. So we have some elements here, and we're going to perform a global combiner. And this global combiner will take all the elements that we have in our P collection and just output one single element. When we do it per key, the same happens, but we output just one element per key. So in this case, all the blues will output this blue element, all the green will output this, all the orange will output all the orange elements, and the same with the green ones. Now I'm going to show you some of the built-in combiners and how we can customize them. Then I will explain something that we call combiner lifting, an optimization that happens in some runners. And to finish this session, combiners and windows. So these are some combiners that are already pre-built on Apache Beam. These are specific for Python. Java has similar ones, but not exactly all of them. The first one is count. This one I already used on my session from yesterday. It's very simple. The name says it counts the elements that we have in a P collection. Mean, that outputs the arithmetic mean of our P collection. Top outputs the n largest or smallest of a P collection, given a comparison to list, make our P collection into a list. To dictionary makes it a dictionary, and latest outputs the latest element that arrived to our P collection. In case that you want to check more building combiners, you can go here and it will take you to the Python documentation for Apache Beam. We can, of course, create our own combiners in case that the built-in ones are not ready and for our use case. And we can do them, of course, globally and per key. Combine globally will be a global combiner, easy to guess, and combine per key will be a combiner per key. Once we are using global combiners, we're going to use our custom combiners, we need to make sure that our logic, when we're using this combiner, is commutative. This is that if we are going to apply a combiner using element A and then element B and combine them together, the result has to be the same as using B and then A. This is the same as in mathematics, and the same with the associative rule. If we combine A with B and the result of that we combine it with C, the result has to be the same that combining A with the result of combining B and C. This is because when we are doing combiners in some different workers, when we have more than one workers, we don't have the same order, and we need to take in account that for our combiner. So the output will be always the same, no matter which worker has which elements on or which order we execute the combines. This is an example of a custom combiner. We're just summing the elements that we have. For example, 5, 5, and 7. If we sum them, we get 12. Now we get this same output and combine it with 3, we get 15. We add 1 and 1, get 2, and combine everything, and we get 17. In the case we do it per key, it's pretty much the same. We combine just the ones that share the same key, and we get the result. One important thing that happens in some of the runners, for example, Dataflow, it's something called combiner lifting. This is an operation that makes the combiner happen first within the worker itself, and then shuffling those elements and performing a final combine. This not only saves a lot of time because we're doing partial aggregation first, but it also avoids issues like hotkey or lazy worker. This is an example of a combine without combiner lifting, in case that this optimization doesn't happen. So we have some elements in our worker. For example, the worker 1 has 8 blues, 2 yellows. The worker 2 has 5 blues, 1 yellow, and 2 green. Yeah. Now we shuffle those elements. We are shuffling those 16 elements, and we need to send all the elements with the same key, in this case, the color. All those need to go to the same worker. So all the blues have to go to one worker, in this case, worker 1. All the yellows have to go to one worker, worker 2, and the same with the greens, worker 2. So we have to shuffle 16 elements. Now that we have all the elements in our worker, we just perform the aggregation, and we get the final result: 55 for blue, 4 for yellow, and 12 for green. This is a bad idea because in case that we have a disproportionate amount of elements with a key, let's say, for example, I have 1 million elements, blues, and just a couple hundred for yellow and green, this will mean that 1 million elements have to go to one worker. And this is going to cause some issues. In the best case scenario, we're going to have to wait for the combined result. So we're going to have to wait for this single worker to perform all the aggregation for blues, which is going to take a long time. And in the worst case scenario, we can get this worker out of memory and the whole pipeline to fail. How can we fix that? We fix it with combiner lifting. Now, instead of shuffling first, we do partial aggregations within the workers themselves, and then we shuffle those. So for example, for worker 1, we just combine the blues and the yellows. We get 36 and 3. We do exactly the same for worker 2, and now we shuffle them up and make a final aggregation with the elements that we got from the previous combine. In this case, we're only shuffling 5 elements. Before, with exactly the same data, we were shuffling 16 elements. Now we're only shuffling 5. And the elements, the result will be exactly the same. You are just avoiding the hotkey, since now one worker can, more than one worker could aggregate things together. In the same example with 1 million workers, 1 million elements with blue, every worker will perform its own small aggregation, and then we will shuffle them, and we don't have to wait for just one worker to aggregate absolutely all the million elements. This combiner lifting happens automatically on the runners. For example, with Dataflow, you don't need to say anything extra apart from the combine in order for you to take advantage of this optimization. Combiners and windows. Combiners also work on a window and trigger basis, of course, and we will get one output for every window, depending on the type of combiner. We need windows and triggers in case that we're using unbounded data. This is because Apache Beam needs to know when you need to finish the aggregation. So the idea is just to split our data in chunks of bounded data. So we use triggers or we use windows, as Reza said during his presentation. So we have an example here of fixed windows, and we're doing, again, the combine globally sum. So all the elements with the same window, we add them up, we get 9, we get 5, and we get 3. So we will get one output per window. In case that we have triggers, the same will apply. We will perform the combine operation within the trigger, and depending of the type of accumulation that we have, if we have accumulating, like it's in this case, we will add this element to the early firing and get the new result. For example, in this window, we have an early firing of 1 and 6 and 5, so we get 6. We get a new element outside of this early firing, and we get 3, so we get 9. And the same with the other windows. To finish off the slides and move to the funny and interesting part of the demo, I'm going to explain the combiner interface, why we need this combiner interface, and what are the operations that we have in there. The motivation is sometimes we need an advanced way of grouping things. We need a more sophisticated accumulator, or we might need to do some pre or post processing. And we might want to change the output types, or we might have a use case that a normal combiner wouldn't work. This combiner interface gives us a lot of control on how things are being grouped together and how we're aggregating our data. We have 4 operations on the combiner interface. We have create accumulator that creates a local accumulator in every worker. We have add input that takes element by element and combines it with the accumulator of the worker. Once we combine the current accumulator with the new input, we return an updated accumulator that is going to be used for the next element. Once all the elements have been partially aggregated, we send them to aggregate them again with something that we call merge accumulators. This takes all the accumulators that we had from the previous step at input and output one single accumulator. Start outputs just takes this last accumulator and performs some final computations to it and returns the actual value that the combine is going to give us. I have an example here that I hope clears things up. So we're again doing the sum. We're creating an accumulator of 0 for every worker. Imagine that we have n workers. I'm going to just show things on the first worker, but the same will apply to every worker, of course. So we have our accumulator 0. Everything that we have on green means that it's an output to the next step. And we take a new element, which is going to be 4. We do 4 plus 0, which is our current accumulator, and we get 4. Now we get 3, and we do 3 plus our current accumulator, which is 4, and we get 7. 2 plus 7 is 9. Now this is going to be the final accumulator for this particular worker. We do the same for all the workers and send these final accumulators for the workers to merge accumulator. So we get 9, we get 4, we get 8. Perform the aggregation again. We define the operation and get 21. This 21 goes to start outputs. And in this example, what I'm doing is just changing the type from one number to a string saying total of 21. So let's now move to the demo, and we will see this on practice. We're going to first install Apache Beam. I forgot to install it before running this. Apologies for that. So let me just go first to explain what we're going to start the demo with. So the first pylon that we're going to have is just using the building combiners. Just as a refresher, we have count that outputs the count of the elements. We have top outputs the n largest or smallest given a comparison, and we have mean that outputs the mean, the arithmetic mean of a P collection. And we can do, of course, both as globally, or we can do it per key. This seems to be installed. Let's run this cell. In case that you get any error when running this cell, you will need to restart the runtime. You can do it with runtime, restart runtime, and you execute this cell again, and it will work fine. So now we have the example with the built-in combiners. We are creating some elements using create, as we did on the previous session. This is because it's easier to use create to generate a P collection than accessing a file system or a database, and it's also faster for you to see what we have as elements. We're creating, imagine this is a table. We're actually creating dictionaries, but just imagine this is a table with a column country, a column population, and a column continent. The next thing we're going to do to those elements is convert them into key values. So we're doing a map function and outputting as a key the continent and as a value the population. Then we're branching this P collection in 4, referencing this create step here as we did on the previous session. And we're going to count them. So we do count globally, and this will output the total elements that we have in our P collection. Then we do the same per key. Now we're going to output the 2 largest elements per key. So we will get the top 2 and a mean per key. We will get the arithmetic mean for, let me make this big, sorry, the arithmetic mean for the arithmetic mean of every continent. Let's run the cell. I'm also printing the graph just so you see that we are actually branching in 4. And let's wait for the pipeline to run. So we get 4 P collections. The total elements was 11. The total elements per key was for Asia 4, for Oceania 1, for Europe 2, and so on. And now we get the top values. So for Asia, we had these 2 values as the top with population. And notice that Oceania only had 1 element, so we only get one value for it. And finally, the arithmetic mean of the population of the data we have. Now let's move to the custom combiners. We can, of course, create them as I told you before. And in this case, I'm going to generate some strings, and I'm going to join them together. This is my combine globally. I'm using a lambda function and just combine them up. And you might be thinking, and you will be right, but Inigo, this is not commutative. It's not the same doing this and then this than the other way around. And you will be completely right. This is not commutative. But I just want to show you, I want to see that we cannot rely on order when we're doing combiners. The order might change depending on the combiners. In this case, since we're running things on a collab, we're using a single thread, so the order will be kept the same. But if you run the same thing, probably with more elements in Dataflow or on Spark, you will get a different order because we will have different workers across. Each one of them will have their own elements, and when you're combining, you cannot control which elements will be joined together. Also, the commutative rule will only apply depending on what you're going to do next. If, for example, this is a bad idea, but for example, I want to join them together to then split them, the output finally, after I join and then split, will be the same. Of course, this is a bad idea. You shouldn't do this to split your boards, but just so you get the idea that sometimes what is actually commutative will depend on the use case. Let's run the cell so you can see that we're actually joining things together. And we get the final result. And in this case, I insist the order is kept the same, but in reality, it shouldn't be. If you have more than one worker, the order will not be kept the same. Now, a combiner per key, we're doing exactly the same, doing a join, but we have, different languages and different lines for this. I noticed that Israel was also using Don Quixote as an example, so I also use it without knowing that. So yeah, the idea again is that the order is not kept the same. Actually, the English version, which is by Shakespeare, is not in order. Just again to insist that we cannot count with keeping the order. Let's run this, and it will be as we did before. We get the joins, but in this case, we get key values. The key being the same key that we introduced to our combine per key, and the value will be the things put together. Finally, we have combiners working by windows. So what I'm doing is creating a dataset with a player column and a score and a timestamp, the same way I did on the previous session. I'm using with timestamp value to add the timestamp to our elements. This is because Apache Beam needs to know when this element was generated, the timestamp metadata. And this is a way just to add in this very easily. So this first X will be the element that we're outputting. In this case, we're outputting absolutely everything. And the second parameter will be the timestamp that Apache Beam has to use. Once we have our elements with the right metadata, I'm going to create some key values just by taking the player and the score. So I am actually dropping the timestamp. I don't need it anymore. We're going to create a window of 60 seconds, so 1 minute. And then I'm going to combine them per key, just summing the score. So I'm summing the values of these key values. I'm also adding this include window info in IV show, just so you can see the windows being executed through interactive runner. Let's execute the cell. So I'm going to move this so we kept the windows in order. So we have Marina that had 1,000 points in the window from 0 to 1 minute. We get Cristina that had 4,000 points in the window from 0 to 1 minute. And in the second window, from 1 minute to 2, Marina had 3,000 points, Cristina 2,000, and Juan 3,000. So if we get the values here, for example, Juan had elements from the window 60 to 120, and if we add Juan's score, we get the 3,000. In case that we want to use windows and global combiners, we need to add something that is called without defaults. This is because the default behavior of the API collection in a global combiner is to output one element for an empty window. This will lead to failure if we don't add this without defaults. So what I'm doing here is just taking the total from before. So sorry, I'm taking the window from before. So I'm just taking the same value as we did after all this operation and after adding the window, and I'm just going to combine them globally. Since I'm going to combine them globally, I just care about the values and I don't care about the keys. So I'm dropping them within this map function. Let's run the cell and see that we should get the right values. So we get 5,000 points from the window from 0 to 1 minute. And from the second window from 1 minute to 2, we get 8,000. And you can see that if I take this out, it's going to complain. Just, you can see that default values are not yet supported in Combine globally. So I wasn't lying. I know that some of you were saying, Inigo, you're probably lying. I'm not. I wouldn't lie to you. So let's now try to create our own combiner. I'm going to do this live, but in case that you want to go through it later, you have the solution over here. So we're going to copy the min function. We're going to do it the same, our own. So I'm creating numbers from 1,000. Actually, let's make it 100. From 0 to 99 included, and I'm going to calculate the average of that. So I'm taking a list of elements, converting it a list, because when we do combines, we're actually taking iterables. Let's make it a list. And I'm just doing summing those elements and dividing them by the length of that particular list. Let's see what happens if I run it. So we get 93.95. Okay, this is definitely not right. It cannot be possible that the average from 0 to 99 is 93. This is way too much. So let's see why this is happening. Let's take this print comment out, and let's print what elements are going to be sent to our combine function. So we see that we at first get 10 elements and we get the right average, so it's going to be 5. But now this element, this output element that we got from this combine, is sent to the next element, the next set of elements. And now we calculate again the average, and we send it again to the next set of elements, and we do it again and again and again and again until we get just one number. Okay, this is definitely not right. We don't want to do this. In this case, number 5.0 has the same weight as the other numbers, but it shouldn't. It should have more weight because it's actually the aggregation of 10 numbers. It should weigh 10 times more than these numbers here. So how can we fix this? We fix it using the combine interface. So let's take this out. Actually, I'm going to just comment it out so you can compare it. I'm going to create a class, and I'm going to create a class. I'm going to call it average function, and I'm going to inherit from a combine function. Now we need to override the 4 operations that we had before. So the first one is create accumulator. I'm going to misspell this so many times. So probably the first run is going to fail because I misspelled some of the function there. We don't need to send anything to this create accumulator. And we need to think what's going to be our accumulator. So we need to keep track of 2 things. We need to keep track of the total sum of the elements and the total elements that we have. So we're going to create a tuple of those. So I'm going to have a sum that is going to be 0, 0, and I'm going to have a count that is going to be 0 again. And just returning this tuple. So let's do sum and count. This is going to be the accumulator that is going to be generated in every worker. Now we need to add elements to this accumulator. So we do def add input in singular, not inputs, input. We do self, and the first parameter has to be the accumulator that we had. So let's do accumulator. And the second has to be our input. Now we need to use our input and update our accumulator. So we have the new value, the new sum is going to be accumulator. We need the first value, the sum, so let's do 0, plus our input, the number that we're introducing. And the new count is going to be our accumulator. We just want the second value, the count, and we're going to increase it by 1. And just return these 2, new sum and new count. So now we are updating our accumulator for every element that it's running. We do this element by element. So we do it first for 1, first for 0, then for 1, then for 2, and so on. Now this, once the ID input is done, it will output one final accumulator, and we need to merge them up. So let's do def merge accumulators. And we need self, and we also need the accumulators. By the way, these names that I'm defining here, you can write whatever you want. I'm just trying to name them according to what they actually do. But if I want to call this, I don't know, blah, 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 it would work either way. I would just use blah, blah, blah here, as long as the order is the same. So first accumulator and then input. That's what I meant, sorry. Now I want to retrieve, so this accumulators is actually a list of all the accumulators that we have across the workers. So I need to take all the values for sum and all the values for count. So let's do all the sums. It's going to be the first value of our list. So let's do x0 for x in accumulators. Actually, let's call it accumulator just so you. So every accumulator that we have in our list of accumulators. I brought it right, yes. And we do the same with the counts. So let's copy this. Counts. Now we want to retrieve the second value of our final of our accumulators within our list of accumulators. So we just do exactly the same, just retrieving the second value of our tuple. And we need to sum both of those up. So this will be now a list of all the sums of all the accumulators that we had, and this will be another list of all the counts of all the accumulators that we had from the previous workers. So just let me do here an example of how it should look like. So for 4 and 2, for example, and 2, and we got 4. So now sums will be a list containing 444 and 222, and counts will be another list of 2 and 4. Now we need to add them up, so we return the sum of the sums, this list over here, and we also retrieve the sum of the counts. Now this is going to be our final accumulator. So we have add everything up, and put them together. Now we need to extract our output, and self once again, and final accumulator. This is the final accumulator that we're getting from merge accumulators. So final accumulator is actually a tuple containing the sum of all the sums and the sum of all the counts. So, okay, this should look like something like this in 666. Oof, I didn't choose this number for this example. The final accumulator should look something like this. Actually, let me just change this to make it less diabolic. So we actually don't want a tuple. We want the average function. So we need to divide one by the other. So we return our final accumulator index 0, the sum, divided by our final accumulator index 1. So in this case will be 665 divided by 6. And if I didn't make any mistake, this would work, but we need to change our average function into a class, and we need to instantiate it as Israel explained in the Pardot. So if I didn't make any mistake, this will work. I probably misspelled something here, but let's check it out. Okay, I didn't make any mistake. This is the right value, 49.9. And if you want to double check that I'm not lying to you and you don't want to make it calculated your own, this cell here so tell us the same value. Okay, yeah, we got it. Yay. In case that you want to try this on your own, I have the solution here. And if you open this, you will see more or less the same function that I did over there. Finally, I'm going to show you an example of streaming. As I said on the previous session, this cell over here will not work for you because Dataflow Run is not imported, and you will need to change the options to reach your own GCP project. But let me go through the code with you a little bit. The first thing I'm doing is reading from a topic, which is the taxi rides real-time topic, which it's a public topic. You don't need to publish anything to it, and it has some information about some taxi rides that are happening on, if I'm not mistaken, New York. So we're reading from that topic, converting it in a dictionary, and we're taking one of the fields that we have in this dictionary is ride status. Ride status have three options. We have pickup, which is a taxi picking up someone. We have en route, which is a taxi driving with someone in the taxi, and we have drop-off, which is someone dropping off the taxi, as you can imagine. We don't care about the ones with en route, so we're filtering those out. And now I'm going to parse our dictionary. What I'm creating is a key value with the key being the right ID, and I have a dictionary over here that has the right status and a timestamp, which is another field that the topics have. We're using a window here that is going to be a session. The session is going to be the right ID. And we're going to do a trigger here. I hope you're familiar with triggers. Reza had a great session. I think it was the first for today. So I hope you get that right. But the idea is that since I know that I'm going to have only two elements, which is going to be one pickup and one drop-off, I'm just triggering the moment I have those two. And to accumulate them, I'm just discarding everything out. I'm going to combine those. I'm actually going to create a list out of those elements. And once I have this list, I'm going to combine those together. So the output of this combined should be a key and a list of two elements. And this map will actually just take the timestamp for drop-off and the timestamp for pickup. So let me go through this code quickly. I'm just taking the key of the element. The dictionary is going to be 1, and I'm creating a new dictionary. The right ID is the key that we had before. This is a new dictionary. And in case that the length of the dictionary is 2, so we have 2 elements in our combine, I'm just going to create 2 new columns, which are going to be called drop-off and pickup in case that the right status is drop off or is pickup. And the values for those keys are going to be the timestamp. In case that the length of the dictionary is not true, I'm just saying that the length was not true and passing those elements. The reason that I need to check for this is because if the moment I create the pipeline, there was some taxi drives happening at that very moment, so there will be elements that will not have pickup. There will be elements that we will start reading their date and routes, so when someone was already on the taxi, and we will only get the drop-off. For example, let's say I create the pipeline at 12:30, and there was someone that took the taxi at 12:20. I will not receive that event on my pipeline, so this way of triggering wouldn't work, and the dictionary will not be 2, but will be 1. And we will have to wait 1 hour for that element to appear, by the way, since we're doing sessions of 1 hour. I have already run this pipeline on my project, so let me show you. We have this one here, the combine. I think it's been running for 7 hours, more or less. So just let me go once again through the code, reading from topic, making a dictionary, filtering then routes out, creating key values, aggregating a session window. We're doing the combine, and we're doing a map over there. This is how the logs look like. So the final row will be our write ID with this unique ID. We will have the timestamp for pickup, which will be this one, and the timestamp for drop-off. By the way, let me move once again. In case that you're wondering what this combine per key is, it's actually the same as a group by key that I saw in the previous slide, in the previous session, but I wanted to make it an actual combine, so I created this function here. But it will be exactly the same as a group by. And I think that has been everything I had to show you. I hope it was clear. Let me see in the questions if I wasn't too fast or if it wasn't too clear. Checking Slack. Can you define, Pierre is asking, can you define multiple keys combined by multiple keys? I am not sure I understand this question. Can you rephrase it, maybe, Pierre? I'm not sure I get it. I will check if you actually write it. Audrey, is this session going late? Yeah, I guess it will depend on where you're attending this. For me, this is 10 p.m. So for me, the answer will be yes. Can you use some fuzzy logic to associate some elements to a key, values fitting in some range? Can it be a task for the ptransform to associate incoming events? I'm not sure if I get it again. I'm so sorry, Pierre. So you can, I'm not sure if I get it, but you can create whatever key you want from the elements. In this, for example, in this case, I was just doing write ID because I know that this was the key I wanted. But if I wanted to say Inigo is the best, I could do, and this will be my key. Okay. Pierre is clarifying. Say you want to key by both order ID and currency. Yes, you could do it. Yes, exactly. Let's say, for example, that I wanted to do. It has to be hashable. That's the one important thing. So, for example, you cannot use tuples there. But for example, if I wanted to, you're saying order ID and currency, I could do something like sorry, I have blocks. Write ID, and since this is a string, I can add it to, let's say, random. So this will be a different key. Or in the case that you propose that was a currency, I could do X plus currency. Now I will be doing the aggregation with multiple keys. And we will have, I call these double keys. I don't know if this is the official term, but this is like when you have two different keys, you want to put them together. In case that you want to perform then another operation, just taking those out. One idea that I had, I don't know if this is the best, but what I did was, let me show you like meta code, what my idea was. So let's make it a test actually. So let's say that I'm grouping by key 1. I'm going to say A1 and value. So I want to group by A and 1. I want to group by this, A and 1. What you can do is create a new element that will be something like A1 and value. Then you aggregate. So you get A aggregated. And then you take the key out and do something like A and whatever you want there, new aggregated. Was this the question that you have, like having multiple keys at once? And I think there are not other questions. Let me check the YouTube. Nothing there. Pierre, can you confirm if this was your question? Okay, awesome.
Yes, he finally answered.
Yeah, I think there's a delay between live for me and live for YouTube.
Yes, there is a delay. Yeah, that's right.
So yeah, that's has been everything. I hope you get the idea of this, and thanks a lot for your time.
Thank you so much, Inigo. And well, if you have other questions, you can keep asking at the Slack, and Inigo is gonna be around, right?
Probably I will go to sleep now because it's rather
Yes,
late.
that's true. It's pretty late for you.
I can answer tomorrow morning.
Tomorrow, yeah, tomorrow. And Inigo is gonna be with us in other sessions.
No, actually, no. I think this is my last one.
Oh, this is your last one?
Yes.
Oh, well, sorry. Well, anyway, stay in touch in the Slack, please.
Sure. Have a good day, everyone.
Good day. Thanks, Inigo. Bye-bye.
Hello, everybody. Welcome to our last talk of this second day of sessions in Beam College. We are here with Ken Knowles, who will talk about state and timer design patterns. And actually, this session was referenced earlier today. There were some questions about how to do exactly this. So we have Ken, who actually was telling me that he was part of or led the development of this feature in Apache Beam some time ago. So it's great. We have an explanation directly from the developer. So it's great to have you, Ken, and please go ahead.
All right, thank you. I guess I'll start by saying that, you know, a lot of this work I did with Reza. So the good parts of this talk are give credit to Reza, and if I mess something up, it is entirely my fault. So yeah, let's start. I'm gonna start actually like at the beginning, and I think this is helpful for me at least. I start by I'm going to talk about things you already know about Beam in order so you understand how I'm thinking about state and timers and how it fits in with the other things. So I'll go quickly through that. So I guess the beginning is you have your graph, right? This is many people have been talking about and showing graphs. It's anything, you have these boxes that are doing computation and arrows between them. And some of the boxes are subgraphs, right? They may contain a number of other transformations, and that's the basic idea of Beam. And there's basically two fundamental operations that I first want to describe and illustrate in sort of my way of thinking about them. You've already heard about them and used them and seen them used in practice, but pardo, parallel do, it's the way that fits in with state and timers is that you first understand that this is doing the same thing to every element, right? This is embarrassingly parallel. It's pretty obvious how you can distribute this across an unlimited number of machines. You know, it's not always map. Sometimes it's filter, or sometimes it's flat map. It outputs like more than one element per input, but it's not, you know, there's no mystery how to implement this, and you don't have to store any state. So that's the one fundamental programming paradigm, right? And the second one that I'll highlight here is just combining, right? Getting all of the elements of some type into the same place so that you can combine them, right? It could be group by key, could be called reduce in MapReduce, could be combine per key. A global combine is the same thing. It just needs to, you know, have one key for everything getting grouped together. And you usually implement this with an associative and commutative operation, and that gives like an execution engine a bunch of options for how it can actually do the computation. It can do 2 layers of reduction so that you don't have to actually read a huge amount of data on one machine. The key here, so I should have explained, you know, squares are inputs, triangles are outputs here, right? And the color here I'm using to indicate the key that you're grouping by. So all the yellow squares, that's those are like one key. So you get those all on one machine, you combine them into a yellow triangle. So it's set up for green squares and red squares. And an important part of this when you're doing like stream processing is that it's sort of implicitly stateful. You're using state under the hood. You do not think about state. You write an associative commutative operation, and then the runner or your data processing engine is able to parallelize it and checkpoint the state. But there is some state involved because you have to wait for all of the elements for a particular key to arrive so that you can know that you have all the data. So sometimes this is called stateful processing. I would call this stateful implementation, and I think it's more helpful to think about since you're not coding anything having to do with state. That's not what I call stateful processing, at least for this talk. Yeah. So that's it. Those are sort of the two fundamental primitives. There's other stuff you can do with Beam, but these are the the two core things, right? It's map and reduce. There's no magic there. And in Beam, we also have windowing. So when you do an aggregation and you're gathering up all the elements for one key for an aggregation, you're also gathering by some event time window. And that makes it sort of automatically work with, you can have huge streams and it can be out of order. And these two primitives still work just fine. So all these quotes are just use cases that sort of work in Beam without you having to do very much. Right, parsing the incoming events and filtering out bad data. It's super easy. I'm not gonna read them all, but grouping elements into sessions involves like some more advanced windowing in Beam. But the basic idea of saying we've got elements, they come in, I choose how I'm gonna group them, I group them, and then I have some output and I do some aggregation like that. That works really well with Beam's sort of P collection, windowed P collection model. And I'm emphasizing that because that's going to be important. So this talk is about when those aren't good enough, of course. We have windows and triggers, and there's been some talks about advanced windowing use cases and how to work with this and think about windowing. And sometimes you're trying to use Beam's windows and triggers, and you're just getting like, it's just not working, right? It doesn't address what you actually need, or it's either too generic, like you don't actually know, like the triggers are very generic. They don't know anything about your data, right? Triggers aren't specific enough for your use case. Or some aggregations are not really an associative commutative operator. And so those don't fit into this model. And the very last quote here, by the way, these are all quotes from me making up what I think your use case could be, right? I've seen a bunch of user cases, and these are just quick summaries of like 4 big categories. But the big one, wanting to output when no data is coming in, right? When you're doing these aggregations, these are just functions over the data, but a lot of streaming use cases actually involve reacting to the fact that a user hasn't actually done anything in a while, or to the fact that your pipeline's been running for a long time. So these are sort of other use cases where the MapReduce, this DAG of MapReduce style operations is not going to apply automatically. So that's state and timers is sort of a hybrid. It's a new primitive operation, right? It's a third fundamental operation for processing data. And I think I should shout out, I think there was another talk on splittable do-fun, which is also a new fundamental pattern, which I just don't have here because you don't need to know about it in this context. But yeah, so I don't want to pretend these are the only patterns, but state and timers is a third pattern, and it's sort of a hybrid of combine and reduce, right? Because what it does, like in Beam, and this is some decision that we made as to how this parallel pattern could work, is for a key and window, you group together all the elements. Like here we have the yellow squares, and we're grouping them all together, and then we feed them to a processor one by one in sort of a single-threaded manner. Because part of Beam, which I know was mentioned earlier, is resist the temptation to do fancy things in your own code or parallelize your own code. We have patterns where you write more or less very simple code. And because you're programming in this pattern, it's going to have some parallelism built in and some scalability built in. So here, all of the elements for a particular key and window, they're all gathered together and they're fed one by one to your processor. And it is able to, do whatever processing it wants on the element, but it can also save some state, which it can access on the next element. And it can set timers, which could cause it to be invoked, cause you to have some callback so you can do some processing when there's no elements showing up. So this, for example, how you would mimic Beam's windowing, perhaps, right? You could set a timer for when a window is done. And when that timer goes off, you can do some processing, right? Even if no elements were coming in. So this is sort of bringing the basics of how Beam is implemented up and giving you a lower level operation you can use. And it's important to call out here, there's no synchronization of the state, right? Because that's the trouble with concurrency, is that when you have to synchronize on state, you have bugs, you have performance problems. And in this case, the pattern of synchronization, exactly how things are parallelized, is already built into the operation. Okay, so now I'm just going to talk through how this works in Beam, this pattern of how you would do this computation. I'm going to start with an example of like why you might use it and how you might use it. It's pretty basic. There's sort of imagine. Let's see. The cloud over here is the some service, right? And if you have used Beam a lot with some distributed runner, you may have already overwhelmed a cloud service with your pipeline. It's very easy to do. If you haven't done it yet, you will, I'm guessing. But yeah, so if you just like make a request per element, for example, right? Spark and Dataflow and Flink and Samza, these can all scale up to, extremely high scale and knock over services. You're not going to want to do that. And if they're billing you, you're not going to want to pay for it. So what you really want to do is just make requests at some reasonable interval. You're processing data so fast, you want to gather up your elements and make fewer requests. So this is an example of how to do that with state and timers. So I'm processing red squares. I only ever process shapes here. So I have my on element, my process element method, and this blue square is my do fun. I'm writing this in boxes and arrows, and later I'll show you Java and Python. But the squares are coming in, right? I can't make one request to this cloud service per red square, or I'm going to overwhelm the service and also spend all my money. So then what I'm going to do is I'm going to set a timer. These elements are coming in. I say, I'm going to save, like, say half a second is an okay amount of latency. I'm going to save half a second of elements, and then I'm going to make a request to the cloud service. I keep saying cloud service. It's a service on the internet. It may not, it's on somebody's cloud. But yeah, so the elements come in, and I know that I'm going to want to make a request with regard to each element. I'm going to want to make a request to the service. So I'm going to buffer those, and this here I'm saving those request metadata that I'll need as triangles off into my state on the side. And in half a second, this timer is going to fire and say, okay, we'll call it on timer. So you will register a callback, and then you'll have some code you can write, and that code can read the state. So now I'm reading all the states, the requests that I buffered up, and I'll make them all in one single round trip, right? And here I'm sending all 4 of these red triangles, and I'm getting back these red circle responses, and then I can output the results of the batched RPC, right? And at the scale of what you're doing, right, in a big data pipeline is, it's not 4, right? We're talking about reducing it by, factors of thousands. So it's pretty important, and even extremely small. Even if you had this timer set for like 10 milliseconds, or even if the timer simply was call me back in the next bundle, you could end up saving a lot. And so that's the example of a kind of thing you would do with data timers. The use cases are very broad because it's a low-level concept with a lot of capabilities. So this is what it looks like. I wanted to show you the sort of the boxes and arrows version before I showed any code. I'm going to flip through a couple slides of code. I don't have a cool notebook, so I'm going to do something even worse than having no code by putting codes on slides. So here's my slide with code. So on the top is what it kind of looks like in Python. I've got a counter. Here we've got, I'm making a stateful dofun, and in Python you extend beam.dofun. And to say I am going to store a counter, you call value state spec, and you can see Java below. We also have something called a value state and a state spec. But in both cases, I'm saying I'm going to store one value, and I'm telling Beam that it's going to be an integer, and then that's just the description of the state you're going to store. And then when in your process element method or your process method in Python, you describe in the parameters to the method what state you're going to read. So here in Python, there's counter equals beam dofun state param counter state. You say, I'm going to read this state, and then you can read it. Might be nothing, so I default it to 0 and then increment it. And in Java, it's the same, but the Java dofun API is annotation based, and so we say, give me the value state with the ID counter. And so this is what it looks like to access one of these state cells. It's a little bit verbose. There's kind of some boilerplate. The reason we did this was because we can essentially do type checking on all of this. Before your pipeline starts running, Beam is going to check that you aren't using state that doesn't exist. I mean, and that the type of the parameter actually matches. In Python, we're not doing the type checking part, right? So in some sense, we're trying to match the language's idioms. I think in Python, we'll check that you're using state that actually exists, and in Java, we'll check that the actual type matches. Timers look similar. They're, I couldn't fit it on one slide, so this is what it looks like in Python. You say, I'm going to have a set a timer so that I can flush state. I'm going to store stuff in state. And I see that after some amount of time, I'm going to output anything that's read in state, for example, right? And I don't want it to sit around for too long. Actually, here I've got a watermark timer, so that's not right. This has to do with if a certain amount of time has happened without any action on this key, right? Like, for example, a user having some activity, but then they've been idle for a certain amount of time, then this timer will fire. And then I'll output whatever data I've buffered. And so here, I won't go over all the code because it's almost identical to how state worked, but the difference is you need a callback, right? You can execute some code when the timer fires. So the on timer method can it can read state, can output values, and it's associated with the timer that you've declared.
Before you
Yeah.
carry on, yes, I wanted to mention that question by Raj. He's asking, how is state and timer different from a window?
Yeah, that's a great question. I will talk a little bit about that. I would say windowing is something that you can implement yourself with state and timers, and Windows, what a window is essentially like a grouping key. It's a partitioning key that has a maximum timestamp so that all the state associated with the window can be discarded. So if you leave all your data, when you read data from the outside world, it's in the global window, and so that doesn't expire. And if you do, you can do state and timer work in the global window, and then your state and your timers will always be valid. And that's roughly how Windows are implemented. But of course, runners can do more interesting and intelligent things. And this is different because you can express more things, right? You can express things that may not be expressible via the window examples, because for windowing in Beam, you can assign an element to a window, which is very much like assigning it a key. You can group by key and window, and so that's another operation you do with Windows, and then Windows can merge. And that's essentially it, right? And so this will be much more fine-grained. You can do things that you would not be able to express with Windows. Before we had state and timers, we actually had a lot of users writing very interesting and complex merging window functions, and sometimes it's much simpler to implement it directly. Often your merge function is supposed to be associative and commutative. This is not required to be associative and commutative. You do have to understand that your data won't be in order, but you can do fairly arbitrary processing, and you're not constrained in the same way. I'm definitely going to talk about the relationship between state and timers and Windows in a couple of different ways. That's, I would say, even most of the rest of this talk. So I'm going to move on, and we'll do more questions after or later. Feel free to put another one in there. I saw the question. I was waiting for the perfect moment to reply. Okay. Okay, so here is one thing to know, since you asked. State is actually already partitioned by window, so we sort of would have a state and timers are per key and per window already. So there's sort of you'd have a cyclic definition if it were defined in terms of Windows, or Windows were defined in terms of state and timers. Here I'm storing like red, green, and yellow. Like these are keys. I'm using colors to represent keys still. So one key is Ken. Let's say I'm writing an app that just tracks every single thing a user does, maybe via their smartphone. I don't know who would do such a thing. So for Ken, I'm using fixed windows of 1 hour, and I'm just like watching what I do. And in each window, I might have some state that is recording, what it seems like I'm mostly doing. So you might notice that in the morning after 9 a.m., after I've no longer have my kids with me. I'm doing some programming, and then I eat lunch, and then in the middle of the night I'm sleeping, right? And each of these stripes is in like the 9 a.m. to 10 a.m. window, the 12 p.m. to 1 p.m. window, and 11. These are all our windows. So when the watermark passes 10 a.m., no more elements are going to arrive, right? The watermark measures whether you're going to ever receive any more data during that event time. And once 10 a.m. is passed, according to watermark, we can discard this data. So having the state per key and window means that we can automatically garbage collect and free up the resources. So you can have an unbounded amount of data, and you can still write, I think one of the philosophies of Beam is you write very simple straight line code. You don't do your own multi-threading. You don't do your own sort of parallel. You don't even think in terms of parallelism. You more think in terms of parallel patterns. And so this is what makes the state and timers paradigm sort of parallel per key and window, and also able to process unbounded data. I'm jealous that Reza is on a flight. That's something I haven't done in quite some time. Okay, so here's where windowing needs to interact well with state and timers. When you're writing Beam pipelines, like I'm going to talk about you having users, but of course, often you're your own user. So your user's view of your transform, like let's say I have this enrichment transform that I showed a few slides ago, where it makes requests to some external service by batching requests. Users don't care about the fact that it uses state and timers. And you, when you're using your transform, are not going to want to keep that in your mind. You're going to want to build some abstraction, right? This is just programming. The important thing here is it needs to work, even if the person, like someone outside your transform, changes how they're windowing their pipeline. So the events come in, they're out of order, but they group it into, say, with grouping them into hours, and your transform needs to just work with the data and output correctly windowed results. So it's the partitioning by key and window makes it more likely that you get this right, and it prevents some kinds of errors, but you still need to be sort of thinking about that. Just to say the same thing another way with another illustration, here are two different pipelines, right? The first one is windowed into fixed windows of 1 hour. Second one is windowed into, say, 30-minute windows sliding by 10 minutes. And what you want, and what is not very difficult to achieve, is that your state and timer, your do fund that uses state and timers, or perhaps in some more complex composite transform, it respects this windowing and it outputs what the user expects, or what you expect, even when you change this, right? Because your pipeline is going to change all the time. It's going to evolve. So, and a third way of talking about how this helps is when we talk about ordering. We talk a lot about how streams are out of order. They come from all over the internet. They're flying in from cell phones that might go through tunnels. And this is on the first example here. We have this faucet of squares that are slightly out of order, and your stateful processing has to be robust to this. What's interesting, right, is also a thing that you need to do is you need to reprocess old data. You need to fix a bug and reprocess it. You need to run experiments on archive data, and this stuff will be sharded. It'll be archived to files. They'll be sharded a particular way. They may be in order in some ways, but not in other ways. But you don't necessarily sort all your data by event timestamp, and certainly across the shards, they won't necessarily be you won't spend the time to merge them, and so you need to be agnostic to the order that the data comes in. And the windowing needs to work in batch as well, right? Batch processing is actually just delayed stream processing. Okay? So it needs to work for both, and that's a fundamental thing to Beam. Okay, there are just a few types of state. I'm just going to highlight there's a number of types of state to optimize for different access patterns. Value state is just saving one piece of data, right? You can read it, you can write it, it has to get serialized and deserialized every time. It's always the whole value. I'm not going to read all of these, but the bag state is important. This is how you would take a bunch of elements and you append them, right? If you're aggregating, you're sort of collecting stuff to be processed later, buffering stuff up, use a bag state, and it's very cheap to add things. You don't have to read the whole thing, add something, and then write the whole thing. And that's why there's a separate access pattern for bag which is the same as a multi-set. Combining state is like that, but when you add something, it can be combined using a combine function, and then sets and maps sort of support the expected operations on sets and maps without having to read the entire value. So, and I'd say the types of state, it's kind of open-ended. We might come up with more, right? I think recently now there's an ordered list state that has a way of like doing range selection on a list of elements. There are two types of timers. I hope it's been emphasized enough that processing time is not event time. These are totally different things and have totally different purposes. Processing time is as your pipeline runs, right? And setting a timer in processing time means like as they're processing, you know, as we're running, maybe I'm driving a UI, I want the UI to refresh, right? So setting timers like that makes sense. Or periodically outputting, like you're doing an aggregation, and it's the same idea, but just generally like if you don't want data to get too stale, or if you just want to like keep some cadence, that's what processing time timers are good for. Event time timers are totally different. They are they have to do with your data, right? And these are relevant in a batch situation too, because your data may show that a user was idle for a certain amount of time, and you're going to want to output based on the fact that that happened, or at the halfway through your event time window, you might want to output your speculative output. And then when a window is over, when a certain special time, like as the user experienced it, occurs, then you want to output. And this event time timers are also how you, how you make sure that you don't accidentally leave any data behind, right? Because when event time is what we use to garbage collect state when we know no more inputs are going to be arriving within a window. Okay. Last conceptual slide is some people might think, hey, thanks for giving us this great other way of doing our processing. I'm only going to use this all the time. You can, but please don't, I guess, because this is, it's lower level. It constrains the data processing engine more. It is, single threading is the opposite of parallelism. So you take exact control of what parallelism is available in your pipeline, and it's a lot of boilerplate. So this is not like, this is sort of an underlying primitive for a lot of stream processors, but you should be able to use like the high level Beam primitives for a bunch of your work, right? And the very complex pipeline, I could imagine state end timers show up. It's not uncommon, but think about it and reach for this when it's the right tool, not just because it's the only tool. Okay, let's see where we're at on timing. So this is where we're transitioning into Reza's example. This is a non-trivial example. It's not too complex, and this is so you can see what kind of code you might write if you're going to say, I've got users, they're watching a video, and I'm going to have these various events that represent moments in the video, like stopping, starting, restarting it, and then these quarter 1, quarter 2, and quarter 3 are events when they're like a viewer reaches a certain point in the video. There's going to be a lot of boilerplate on these slides. I'm going Java because that's what it sort of just came first. I haven't ported it to Python yet. And you may have to write a lot of boilerplate using state and timers. It's very low level. And always remember that order is not guaranteed. We're not sorting events as they come in. Okay, so as a user watches a video, I'm going to have these rules. We're going to have a few rules about these events. These are the events I just described. We're starting the video, progressing through the video, hitting the end of the video. The user can also pause, restart, and stop. What do we want to know about users watching these videos? Well, here are the four rules. Rule 0 is when the window is expiring or when the video finished and there's been 10 minutes with no activity, we're going to output. Rule number 1, we're going to output every time we see somebody make it to the third quarter. We're going to call that a view. We're going to say, okay, we're going to go pay Ken for the fact that somebody watched his video. Rule 2 is to output when you see a stop. Right, the user stops the video and then sort of abandons it for 2 minutes. And then rule 3 is when there's multiple restarts without any quarter. being passed. So that sort of implies that the page is being refreshed. Maybe they're like, hey, I can't get it to play. So rule 0 is going to use one timer and one piece of state. I'm going to record, I'm going to have all these events coming in, and I'm going to record for each user what is the maximum timestamp that I've seen. And I'm also going to keep track of this timer for when we have an end and the no activity for 10 minutes, right? And so by when this timer fires, I'm going to be able to check, like, has it been 10 minutes since the maximum timestamp? So when I access this timer and state cell in a DoFun, this is what the declaration looks like. I won't read it over, but you can see that I have a TTL timer and the maximum timestamp observed as a value state. And the body of the function, I'm going to take the max of the current timestamp that an element has and the one that we've seen so far. I'm going to write that to state, and then I'm going to set a timer for 10 minutes after that. So one thing to note, the TTL timer is reset every time this is called. So every time I get an element, I'm overwriting the prior timer. This is cheap. This is free. In general, right, this is all done, and when a bundle is committed, it does reset the timer, but it's fine to do it every element. And we're just making sure by writing it to state that we always, across all bundles, we're always writing the actual maximum timestamp observed. Note that I do a write and then a read here, even though I have the value available. When the timer fires, here I'm taking the key, so I know what user it was, and then I'm saying GC happened, like where this view is done for that key. And that's that simple. Because I've reset the timer, when it does fire, that means nothing else has actually happened since the last time it was set. I'm noticing that we're short on time, so I actually think that working through the rest of this example, I'm okay with going over, but I think I'm going to skip to the interesting rule. Actually, the interesting rule, I think, is, let's do rule 2, which is the rules are all very roughly the same, but so this is alpha when we see a stop, but no activity for 2 more minutes. Right? No, that's not. Now I'm waffling. So let's just do this one. So I'm still using the maximum timestamp observed, and now I have another timer for rule 2. And this one is actually essentially the same as rule 0. So I grabbed the wrong one. What I'm doing here when the timer fires is I'm checking whether or not the timestamp for this timer is after the maximum timestamp observed in order to output that rule 2 is what happened. Right? Interesting. I'm going to actually zip ahead here. Yeah, I'm actually going to call it because I know we're out of time, and I want to have plenty of time for questions. And I'm sorry, I chose rule 2. That was a bad call. It's almost the same as rule 0. But I'll stop here. I cannot hear you.
Hello. Sorry, I was muted. My bad. Okay. So you already addressed the question from Raj about state and timer being different from a window. And we have another question from Pierre Overholzer asking, on which database is state persisted on Dataflow? Can that be configured? And is there any limit on size?
Yeah, it depends. Is the answer. So on Dataflow, so each is deliberately, of course, runner dependent. On Dataflow, it depends in streaming mode. The state is stored in the same database called Windmill, which is, you can find references to Windmill throughout the Beam code base as well. So it's stored in the same system that stores the element data, and which also manages the timers that implement windowing. So it's sort of the same underlying implementation as just element processing in streaming mode. And in batch, it's processed in a different way, because in batch, you tend to actually shard into your keys, and you can process a whole key at a time. And so it's important actually for every runner to decide to have different implementations that work for the particular mode of processing. So if you take a whole key and all the windows for that key and you process it all at once and you try to actually store all of that state, you're going to blow memory. So in batch, you actually, the best way to do huge bundles is to sort of sort things and garbage collect state halfway through processing a bundle. And so, yeah, I hope that answers the question. So it's windmill in streaming, and in batch, it's sort of a hybrid of memory and disk.
Okay. Pradeep asks us, how are the worker threads associated with bundles and elements?
So every runner has their own notion of what what a worker thread is, and it could be a sub-process in the case of like Python, where you actually don't have a meaningful threading. So the answer is that I think the important thing is that a runner is required to call your DoFun in a way that a given instance of your DoFun is not ever used concurrently. So when you're using state and timers, you are sure that one DoFun and one key and window is used single-threaded, right? One process, one thread, no concurrency of any sort. And a bundle, however, can include elements from across like many keys and many windows. A bundle is actually just the unit of commit, right? It means like it's the input being committed to the resulting output. I guess I want to say that the threads and bundles are not like strictly related in the Beam model.
Okay. Next question by Raj. In the state store, do you keep history of state for a data key, or just the latest wheels timer is running as? Oh, give me a second. I don't know if there's a typo. So in the state store, do you keep history of state for a data key, or just the latest while timer is running, assuming the former in the case order would be important when processing on expiry? Oh, I'm going to paste that for you in the chat window.
Yeah, I have Slack open. I see this question. Okay. It's if I understand it, it's important to say that timers are also single-threaded with process element. And in fact, I should mention this. I believe timers are processed after the elements in a bundle. There's been some discussions on this, but I think that's the answer. There's no concurrency between like a timer firing, and so there's no need to store. We don't store state history. Certainly, like state is committed when a bundle finishes. Like the bundle is the unit of commitment, right? So indeed, if there's a failure while processing a bundle, everything that happened has to be rolled back, and so the state won't have been committed yet. But within a bundle, all the elements and timers for a given key and window are processed. It's single-threaded. So I hope that answers that question.
Okay, I see Pierre is probably typing a question. Let me see if he commits it. In the meantime,
sure.
I'll go check the YouTube to see if we have any other questions. Okay, there's a question by Pierre. Can I use another database than Windmill for state keeping and use an archive data store instead of whatever uses GCP like GCS or BigQuery?
Well, so I'll say that like GCS and BigQuery are not choices that you would want, I think, for this purpose. So the important thing, what do I want to say? The state needs to be tightly integrated with the exactly once processing and bundle processing. You can, if you have your own, something a user can do, right? Windmill is implemented sort of, it's what do I want to say? You can store your own state in another database yourself, right? You could, but it won't be as tightly integrated with bundle processing, and it'll probably have higher overhead, right? Certainly there are users and there are situations where maybe the thing that works best for you is to, as you're processing elements, write a bunch of data to your own Bigtable instance, for example, your own Bigtable cluster. The problem with that, of course, is like if a bundle fails, you don't have any way to properly roll that back easily. And so you really want to treat that, I would say, we have a bunch of connectors for that. Like when you want to write to an external data storage system, their Beam has connectors which are very aware of, they're very aware of the difference in like Beam's commit protocol and the external systems consistency.
Okay. There's another question by Jeff McCarroll. As a follow-up, what are the recommended patterns for externalizing views of state?
Yeah, I don't have a ready answer. I feel there may be somebody may be familiar. Flink has this concept of sort of queryable state, where you take something that you're aggregating in state and you make it available, via API access, and you can view the status of that. Beam doesn't have anything like that. And I think that's probably an interesting avenue to pursue. But in general, I think, taking your state and just outputting it to a P collection and then writing it to a storage system, there's already connectors that do that. And so, which is, that has a lot more overhead. So exploring how to directly expose the state is interesting. You need a lot of layers to make it make it work for all the different runners. It needs to be like, what are the fundamental concepts around that? For example, some runners may not ever materialize state at all. And so if you ask for them to serve it, that's going to have like an enormous overhead and change everything about how your pipeline runs. That's my non-answer. There are no recommended patterns for externalizing views of state. I don't have a ready answer. I think that's kind of interesting. I'd love it if you wrote that to the Beam user list for a discussion, or kept chatting in Slack. But I don't think that there's a recommendation other than writing it to some external storage system that you'll then build a UI on top of or whatnot.
Okay, well, I think we're done with all the questions. Thank you so much, Ken. Thank you for the presentation and your time and sharing this. Thank you, everybody, for joining. We'll be back tomorrow with more sessions on Apache Beam. And we have one last question. And yeah, we have a couple of minutes. One last question from Raj. Yeah, is the state centralized or distributed? Basically,
you're asking. Stop worrying about that. That's what I want to say. Well, which is to say, like, it depends on the engine you're using, right? And it is, I will say, it's persistent is the answer. So, distributed is the right answer, but that's. I hope that's the right answer. It's sort of like this is such a conceptual talk that's not talking about a specific engine, but each engine has their own way of committing state and keeping it durable. And it is as durable and reliable as your data, right? The underlying mechanism should be the same, basically, as how aggregations are stored. In general, almost every engine uses the same mechanism for aggregations and state.
Okay. Well, thank you so much then, Ken. And we'll continue tomorrow at the same time we've started yesterday and today. Tomorrow, actually, The first session will be on custom containers, and we'll describe how to use Docker container images to customize the execution environment for your Beam pipeline. So please join us tomorrow, and we will send you a survey. We will email you and post in the Slack a survey so that you can let us know how we're doing, what you've liked of the sessions that we've done so far, and what we can improve for the next week. Okay, thank you, Ken, and see you tomorrow, everybody.
Thank you.